Board on this. Amazing. Okay. So talking about airway management, when we talk about our, our patient evaluations, assessments, or you bust out your patient assessment for medical or trauma, after you establish scene safety and your PPE is on, and we are going to take care of our patient, our first priority is ABCs, and the A stands for airway, and there's a reason. It's because it's extremely important. Of course, this isn't going to work. Okay, there we go. Okay, so let's talk about the anatomy first. Your airway can be separated into two different groups. Your upper airway and your lower airway. Your upper airway consists of your nasopharynx, your oropharynx, and your laryngopharynx, or your larynx, which is much easier to say. That's these three spaces right here that sit above your trachea. Okay, so just behind your nasal passage, your the inside of your mouth, and then just beyond your epiglottis. Okay. The responsibility of your upper airway is to warm and humidify the air that you're breathing in, as well as filter the air that you're breathing in. Obviously, it's not a perfect filter, but it does filter quite a bit in order to keep any foreign anything from getting into your lungs, okay? The other thing is that these little folds right here, these are called your turbinates. And these are what make it possible for you to smell. Okay. The surface area on these are connect to your oh my gosh, I'm going to say the wrong thing. I think your olfactory nerve. It's one of your cranial nerves, and that makes it possible for your brain to register smell. If you were to look at a similar pet of like the nose of a dog, they have tons of turbinates, and that is why their sense of smell is so much stronger than ours is. It's for those turbinates. Okay, so yeah, upper airway is to filter that air, warm and humidify it, okay, before it goes to our lower airway. Once we get to our lower airway, we enter our trachea. Okay, that's that big, long, also known as your windpipe. It is covered in muscle, but also has those bands of cartilage right there in order to stabilize it, give it structure, but also make it so that you can move. It can expand, it can move. So that's why it's not completely made of cartilage. Okay. Your trachea ends at your carina. That's this bifurcation right here. So your trachea goes down in between your lungs, and then it bifurcates at the carina into your bronchi, into your primary bronchi, which is that first stem, and then your secondary bronchi, which is the next few stems, which are all still made of that muscle and the cartilage, okay? But once you bifurcate more into your bronchioles, you don't have that cartilage anymore. You just have the smooth muscle, okay? So trachea bifurcates at the carina into our primary bronchi, then to our secondary bronchi, then to our bronchioles, okay? And the main purpose of the lower airway is to oxygenate. It is to provide gas exchange for the body, to give oxygen to blood and tissues, and then to take the waste products of CO2 and exhale it from the body. And that's done here at the alveoli. Okay, so these alveoli, you can see this is a lot smaller. So it does still have some cartilage, but it's very small and it's much more flexible, okay? Your alveoli are these portions right here, these big balloony looking things, okay? And each individual one of these is an alveolar sac. And the point of these is your oxygen comes in through your windpipe to the bronchi, bronchioles, and then into these sacs. These sacs are hollow. And then it expands your alveoli slightly, okay, in order to increase that surface area, which allows for more gas exchange to happen, okay? And then the membrane in between your alveoli to your blood vessels will exchange the gas through just simple diffusion across the membrane. It'll push oxygen from high concentration to lower concentration areas, which is going to make it attached to your hemoglobin on your red blood cells. And then your CO2 is going to come in and it's going to detach from your hemoglobin because it's in high concentration. It's going to move to the lower concentration areas, which are inside your alveoli. And that is how it then exhales it out of your body. Okay. Your alveoli has a couple different kinds of cells, and one of them creates surfactant. Surfactant is the fancy word for alveolar lube. It's what makes it so that you can expand the surface area of your alveoli without it grating against anything else, okay? And you need that surfactant in order for the alveoli to expand. Otherwise, it becomes extremely painful. Your alveoli can become distended indefinitely. You'll see that kind of those more the extremely blown up versions of alveoli that just kind of stay there. They lose their elasticity. You'll see that in like emphysema or COPD. Okay, we talked about those membranes. That is just the surface of your alveolar sac that interfaces with your blood vessels. Okay, and in that is where gas exchange happens through diffusion. And we'll talk a little bit more about that later. Okay. Okay. It may come as a surprise to you, but breathing is muy importante. Okay. It is very, very important. That's why it's number one on our treatments after life threats in our assessments. And it's because our heart and lungs work together to supply oxygen to and remove carbon dioxide from the body. Okay, so looking at the need for adequate ventilation, which is simply the movement of air through our lungs, if we go without adequate ventilation, without oxygen for, up to a minute, it causes some cardiac irritability. So if anybody tries to hold their breath underwater, you'll probably find that it's a little uncomfortable. You'll get some burning. Your heart will probably start to race because it's wondering what the heck you're trying to do. But it's nothing too serious, okay? If it's for anything under about 4 minutes, the brain damage is pretty unlikely. But when you get to about 4 to 6 minutes without oxygen, brain damage becomes pretty possible. 6 to 10 minutes, your brain damage is likely. And anything, oh, that should be the other way around. That's my bad. Anything over 10 minutes, any brain damage that is done is irreversible. Okay. So that's why it's so important for us to manage the airway first. Because it doesn't matter if we're pumping blood or if their blood is pumping, if it doesn't have anything to pump through the system, then it can't oxygenate the cells, it can't oxygenate the tissues, and everything starts to just die. Okay. So yes, proper ventilation, oxygen. All right. So we're going to see lots of words and lots of numbers. Okay. I'll tell you what is the most important to remember about this information because I understand there's just a lot here on this page. Okay. And also colors. I need colors in order to remember things. So hopefully that helps some of you. All right, when talking about the mechanics of breathing, this is all about pressure differences, okay? The first thing to remember is that your atmospheric pressure, here, letter C, is the pressure of air outside the body. And that we cannot control. That is like our ground zero. Okay. So it says about 760 millimeters of mercury here. You can also kind of remember it as zero. It's just our ground level doesn't change. Everything is compared to atmospheric pressure. Okay. So when we look at our thoracic cavity, we have our ribs and our intercostal muscles here, but then lining the inside of our thoracic cavity is what's called the parietal pleura. Okay, it's just a lining that protects the chest wall, and you can, let's see, I'm trying to remember. I can't remember how I remembered that. So I don't know. That was super unhelpful. Sorry. So parietal pleura is lining the inside of your chest cavity, or the chest wall. And then when you get to the lungs and everything inside your chest cavity, it is now lined with visceral pleura. Okay. Now, something important to understand is even though right here it's disconnected, this is actually the same lining. It just folds when it gets to the top and the bottom. That's just from the point that it's no longer the chest wall and now it's, the lungs, it changes from parietal to visceral pleura. The other thing to remember is even though this looks like a very large gap, the space between your parietal and your visceral pleura is about like the space between like your hand and a glove. Okay. And in between the parietal and the visceral pleura is pleural fluid. And that pleural fluid is there in order to prevent the parietal and visceral pleura from rubbing up against each other. And without that fluid, you'll get what's called pleurisy, and that is extremely painful. It is so painful to breathe. So having even just the thinnest layer of pleural fluid is really important to keep those from rubbing up against each other. Okay, so they're very thin layers. They sit very close together, but they are still layers, and each of them is very important. Okay. So when talking about the pressures in our thoracic cavity versus the atmosphere, we're going to start with at rest. Okay, so this is, I have just inhaled and I have just exhaled. Okay, and so at that point where you finished exhaling, but it's before you have to inhale again, that is at rest. Okay, and at that point, our intrapulmonary pressure, which is right here, this is inside the lungs, is 760 millimeters of mercury. Okay, and you'll see me put that in as P-pul, okay? So your intrapulmonary pressure. Your intrapleural pressure, which is in between the lungs and the chest wall, is about 756 millimeters of mercury, okay? And then, of course, your atmospheric pressure is about 760 millimeters of mercury, okay? So those are pretty big numbers. But if we translate it into the differences, then they become a little bit more manageable to remember. So when I say translate it into differences, if we look at our transpulmonary pressure, which is D, that's our pulmonary pressure difference between intrapulmonary, what's inside our lungs, and intrapleural, which is outside our lungs but inside our chest cavity. Okay, and the pressure difference between these two is about 4 millimeters of mercury. Okay, and that makes sense because we're going from 760 inside the lungs to 756 outside the lungs. Okay, and so the difference is 4. If we go from intrapleural to atmospheric, that's going from 756 to 760, okay? And 756 minus 760 is -4, okay? And that's our transthoracic pressure. That's in between our thoracic cavity and the atmosphere, okay? That's the difference of pressure there. And then our transrespiratory pressure is the pressure between inside our lungs and the atmosphere. And at rest, you can see they're both the same. A and C are the same, which means our transrespiratory pressure is going to be 0 millimeters of mercury. So that makes sense. That is a lot so far. Is everybody keeping up? Do we still feel good? For now, amazing. Okay. So, at rest, atmosphere is 760. Inside the lungs is 760. In between the lungs and the chest wall is 756. Okay. Hello. Okay. So I told you guys that the intrapleural pressure is negative. That's the pressure between the space, the thoracic cavity, and the difference between the pressure in the thoracic cavity and the atmosphere. Okay. And it's negative. It's -4, since all pressure is compared to the atmospheric pressure. Why? Okay. So I'm going to explain why and just hold on to these 3 reasons. And then I'll bring them up again as we go into how the pressures change when you inhale versus exhale, quiet versus forced. Okay. So first thing to remember is the elasticity of the lungs. Your lungs are constantly pulling the visceral pleura, which is the pleural lining up against the lungs. It's constantly pulling that pleura in and away from the parietal pleura, okay, which draws the lungs in. And if you remember, those layers are very close together and they're only separated by that pleural fluid. And the way I kind of remember that is if anybody has worn mainly my females, although hey, I won't judge. If you've worn a one-piece swimsuit or even just a wet shirt, okay, and it's wet and and your whole body is just sopping wet and it's clinging to your skin, okay. If anybody has tried to take it, like pinch it at their stomach and pull it away, what ends up happening? What happens to the fabric? Does it just come off? Does it separate very easily from your skin? What happens? Nobody's worn wet clothes before?
Kind of suctions to you.
Yeah, it kind of suctions to you. Okay. It kind of makes that tent kind of look to it, right? Because that water, that fluid is wanting to keep that layer of clothing close to the skin. Okay. And that ends up changing when you add air to it. Okay. Because as soon as air enters that space, the suction's gone and it becomes much more easy to separate. Okay. And in this situation with your lungs, that becomes a problem when you have a pneumothorax, right? When you introduce air into the lung cavity, whether it's from a hole in the chest wall or a hole in the lung wall, that's going to cause that separation. And what happens is the elasticity of the lungs is still there. It's going to pull the lungs away from the parietal wall, but now it's successful because there's air in the thoracic cavity, which then completely displaces all of the pressure gradient and how much pressure is in the lungs, and that's what makes it so difficult and to a point impossible to breathe when that happens. Okay, so that elasticity of the lung is pulling the visceral pleura away from the parietal pleura, but the pleural fluid keeps them suctioned together And that is what pulls your lungs in, and that consequently pulls your chest wall in as well. Okay. So that pressure is happening constantly. Okay. On top of that is the surface tension. The surface tension just in your lungs and in the alveoli, just in general, is constantly drawing the lungs in to collapse the alveoli. Okay. It's like if you blow up a balloon and you don't put a knot in it and you just let it go, what's it instantly going to do? All of the air is going to flow out of the balloon and it's going to deflate. Okay. And it's because of that elasticity and that surface tension. And then lastly, there's the elasticity of the chest wall. Okay. And that is constantly trying to pull the parietal pleura out and away from the visceral pleura, which pulls the chest out. Okay. So you have constant tension between your lungs and your chest wall and the surface tension, all trying to pull against each other in order to equalize the pressure between your lungs, your intrapleural space, and the atmosphere. Okay. And it's that constant pressure, like fighting over pressure, that makes it possible for us to breathe. Okay. Another unofficial reason is gravity. Okay. Gravity naturally wants our diaphragm to pull down. And so it's going to try pulling down on the bottom of our lungs. And again, that parietal pleura is there lining that. And the pleural fluid is keeping it suction to the visceral pleura, right? And so even gravity is trying to pull your lungs down in order to expand the space, okay? So our three reasons that our body is constantly under pressure, our thoracic cavity is under pressure, is the elasticity of the lungs trying to pull everything in, the elasticity of the chest wall trying to pull everything out, and the surface tension in between those both, and the alveoli that's just trying to pull everything into the lungs, okay? So if we look at Boyle's law, this equation just says that if you increase the pressure, then you decrease the volume, okay? And the vice versa is true. If you increase volume, then you're decreasing the pressure, okay? So with the three sources of tension constantly trying to force the thoracic cavity open, or increase the volume within the thoracic cavity, then the pressure is naturally decreasing. And that is what is making the intrapleural pressure negative. Okay. The -4. All right. And then just to review, that -4 is the difference in pressure between the thoracic cavity outside the lung, but inside the chest wall, and the atmosphere. Okay. That is -4 because the body is constantly trying to increase the volume within the thoracic cavity, which is causing the pressure to drop. Okay. Now, that's a lot of information. Let's talk about it in some real time. Okay. So quiet inspiration. I'm going to talk about quiet versus forced. Our quiet inspiration is just kind of what you're doing when you're just breathing. Just, nobody notices. I'm just breathing. I'm just, doing my oxygen and carbon dioxide gas exchange. Quiet inspiration is pretty chill. And it doesn't require a ton of effort. So during our quiet inspiration, what happens? Why does it keep doing that? What happens is our external intercostals, which are these muscles here, okay, are constantly pulling the ribs up and out. Hang on. Okay, constantly pulling the ribs up and out to expand the volume in the chest cavity, and the diaphragm contracts. Okay, the diaphragm contracts, which then which pulls the diaphragm away from the lungs, But because of that pleural fluid, that suctioning is happening, and so it's increasing the volume within the lungs, okay? So that thoracic volume increases. And what that does to your intrapulmonary pressure, which is the pressure inside your lungs, is it decreases by 1 millimeter of mercury, okay? And your intrapleural pressure decreases by 2, okay? So now instead of 760 millimeters of mercury, it's 759. And instead of 756 millimeters of mercury, it's 754, okay? That causes our transpulmonary pressure to increase, okay, to 5 millimeters of mercury. And that transpulmonary pressure is the difference in pressure between inside the lungs and outside the lungs. So that increases, but our transthoracic pressure, which is in between the thoracic cavity and the atmosphere, decreases more. And so it's now, instead of -4, it is now -6. Okay, so it's decreased in pressure, which then makes our transrespiratory pressure, which is the pressure difference between the lungs and the atmosphere, now it's not 0 anymore. It's now -1 millimeters of mercury. Okay, so before inside our lungs it was 760 and the atmosphere was 760. Now during quiet inspiration, we're taking a quiet breath in. And that is causing, because we're increasing the volume in our thoracic cavity, that's causing the pressure to drop inside the thoracic cavity by 1 millimeter of mercury, okay? And that negative pressure makes it possible for air to be forced from the atmosphere into our lungs, okay? Because our body is constantly trying to equalize the pressure. So it's now -1, and our body's like, oh no, we need to make it equal to the atmospheric pressure again. And so we're going to force air into the lung. It's kind of like a vacuum. We're going to force air into the lungs in order to equalize it with the atmosphere. Okay. And so we'll reach that point, we'll equalize, and that'll be the top of our inspiration. That'll be the top of our inhaled breath. And at that point, we will go into quiet expiration. Okay. And everything equalizes again, and it wants to go back to rest and things like that, okay? So, but right now, we're during quiet inhalation. We've got air forced from the atmosphere and into the lungs, okay? Now, what if it's forced inspiration, okay? This is when you're taking a big, deep breath in, all right? Or maybe you're having difficulty breathing. We'll see this in asthma attacks, or if something has happened that's disrupted the pressure gradient within the thoracic cavity. People will start to force their inspiration in order to increase or decrease the pressure within their thoracic cavity, okay? So in addition to the external intercostals and the diaphragm, now we're going to be using our sternocleidomastoid muscle, our scalene muscles, and our pectoralis minor muscles to help us breathe, okay? The sternocleidomastoid muscle attaches to 3 different spots, okay? And so what I want to do is I want someone to tell me those 3 spots based off of this word, sternocleidomastoid, okay? Who is brave enough to give some medical terminology a try?
I think I might have it.
Okay, go ahead.
The sternum is one guess.
Mm-hmm.
I believe the cleido is the clavicle,
Mm-hmm.
and then the mastoid, I believe, is the jaw,
Yeah, close
or
to.
below it.
Yeah. Mm-hmm. Yeah, very good. So sternum, cledo is that clavicle, okay? And then mastoid is an area close to your jaw, okay? Um, I want to say the mastoid process, but now that I'm saying it, I'm not entirely certain. So take that with a grain of salt. But close to your jaw, up here, It's attached down here to your sternum and to your clavicle. Okay. So now when we're forcing inspiration, this muscle is contracting, and that is forcing our chest cavity or our chest wall open even more than it was in the first place. Okay. Our scalenes are about right here. They're technically neck muscles, but they kind of come off the neck. They're pretty small, but they're powerful. Okay. Same thing. We're pulling that chest wall. We're trying to increase the volume inside the chest cavity. And then our pectoralis minor sits underneath the pectoralis major muscles that are inside your pectorals. Okay. So this added effort brings that pulmonary pressure, the intrapulmonary pressure, down to 758. Okay. So this is the pressure inside your lungs, which at rest is 760. During quiet inspiration is 759. And now during forced inspiration, we've brought it down again to 758. Okay, which further decreases the pressure, which in turn forces more air into the lungs. Because what happens when we decrease the pressure? What happens to the volume?
Goes up.
It increases. Okay, so just at the same time, if we're increasing volume, it's decreasing pressure. If our body is decreasing pressure, it's going to be increasing the volume. Okay. All right. During quiet expiration, this one's kind of easy. During quiet expiration, it's a very passive process, which means no muscles are being used. Okay. We are entirely dependent on the elasticity of our lungs. Okay. So I have quietly inhaled. And now I'm just going to let my breath go, and I don't have to do anything. And everything collapses. Okay. Which increases that pressure again. Okay. So the stretch receptors from the thorax send inhibitory signals to the brain and the medulla, which we'll talk about more in just a minute. These signal the muscles of inspiration to relax, no longer forcing the thoracic cavity to be expanded. Volume decreases, meaning pressure increases until all of the pressures return to their at-rest values. Okay, so you'll see these numbers, though, are just a little bit different than our at-rest values. It's because we overcompensate once we exhale. And then after we overcompensate and get all of that carbon dioxide out, we return to the at-rest pressure. Okay. So once we are in quiet expiration, the only number that's different from our at rest is our intrapulmonary pressure inside our lungs, which is 761 instead of 760, because we are pushing gas outside of the lungs and into the atmosphere. Okay. We don't want it to be equal. Otherwise, nothing will happen. We're at rest. So we want it to be just more. We want our pressure to be just barely increased in order to just barely decrease the volume in our chest in order to push that gas out. Okay. But our intrapulmonary or our intrapleural pressure is back to 756, which is what it's normally at rest. Okay. Forced expiration, we are now engaging our abdominal wall muscles and our internal intercostals. Okay. So our external intercostals are pulling the ribs up and out. Okay. In order to expand the chest wall. Our internal intercostals are pulling the ribs down and in order to decrease the volume inside the chest cavity. Okay. And so we're doing this to force air out of our body. And so that is going to change the pressure even more. Okay. Both of these muscles are forcing the thoracic cavity to decrease in volume, which is forcing more air out than it would in quiet expiration. Okay. So instead of in quiet expiration, where our intrapulmonary pressure is 761, it's now 762. Okay. So we have that extra millimeter of mercury of pressure. But on top of that, Our intrapleural pressure is now 757 instead of 756. So not only have we added 1 to the pressure inside our lungs, but we have added 1 millimeter of mercury to the inside our chest cavity wall, or our chest cavity. Okay. So now we have added 2 total millimeters of mercury to our pressure in order to decrease the volume in our chest cavity even further. Okay. All right. So in talking about that, here, I'll go back there. Are there any questions? It's a lot. It's a lot of numbers. It's a lot of words. Actually, I'm going to go back here.
I have a question.
Yep, go for it.
So if quiet inspiration is a passive process, then forced inspiration is an active process or not?
Correct. Yeah. So passive just means we're not engaging any of our muscles. We're simply relying on the elasticity. So this elasticity of the lungs, in order to collapse the lungs, to decrease the volume. And that allows us to expire the air that's inside our lungs. Okay. So, the other difference between quiet versus forced expiration, quiet versus forced anything, is that there's always residual or reserve volume left over if you're engaging in quiet inspiration or quiet expiration. So when you're just breathing normally, is that as much air as you can take in, or can you take in even more air? We can take in even more air, right? So I just small inhale, but if I go, that is how much more volume in my lungs that I can fill with air to increase gas exchange. Okay. So that is more active. That's forced inspiration when I'm taking a bigger breath. Whereas if I do quiet expiration, I'm just letting everything collapse and it's just pushing some of the air out of my lungs. Whereas if I force myself to expire, if I go, I'm pushing even more air out of my lungs by engaging the abdominal wall muscles and my internal intercostals. Okay. So I actually kind of want you guys to do that with me. All right. We're going to take a small breath in. Small breath. That's quiet inspiration. Big breath in. That's forced inspiration. And then quiet expiration, we're just going to let it out. And then forced expiration, we're going to push it all out. Okay. And that is exploring the entire range of your lung capacity. Okay. Your tidal volume inside your lungs is everything, is all the room that you have inside your lungs. Or sorry, that's not your tidal volume, that's your capacity. Your capacity is all of the space that you have in your lungs that you can fit air into. That is your capacity. And that is about 1,200 milliliters. Okay. Your tidal volume is how much you breathe between inspiration and expiration. Okay. And that is about 600. All right. So that's like half. And you have the residual, 300 on either side, if you think about it that way, that you can increase. You can take in up to, 900 mils or whatever of air into your lungs, or expire even more air out of your lungs because you have a capacity. But our tidal volume is what we normally breathe in and out. Okay. So lots of words, lots of numbers. I want to review real quick right here. Okay. So we have, oh, wrong one. This one. This is our normal at rest. Okay. Inside our lungs is how many millimeters of mercury?
760.
760. Okay. And how many are outside in the atmosphere?
The same.
The same, which means our trans-respiratory pressure, or the difference between those two pressures, is what?
4. 0, I mean, sorry.
0. It's okay. It's 0. There is no difference, and so there's no there's no movement of air because there's no difference in pressure. It's neither high or low, okay? But if we look at our intrapleural pressure, what is that?
756.
756. Thanks, Glenn. I appreciate you. It may surprise you all, but it is right here on the page. Okay, it's 756. So what does that make our transpulmonary pressure? So the pressure difference between inside our lungs and outside our lungs.
That's our 4.
That's your 4 millimeters of mercury, okay? But a little bit more important is the difference in pressure between your chest cavity and the atmosphere, okay? So we have 756 inside and 760 outside. What is that?
That's your -4.
That's your -4. That's your transthoracic pressure, okay? So when we have quiet inspiration, everything is moving by like barely anything, right? Okay, so everything is moving by barely anything because your muscles are engaged. Your inside your lungs is now 759. It's only changed by 1. It's gone down. Okay, we've decreased pressure here. Inside our chest cavity, it's decreased by 2. Okay. And so that means our transthoracic pressure in between our chest cavity and the atmosphere, because the atmosphere hasn't changed, it's still 760, is now -6. It's gone down, okay, by 2. And that means everything, the difference between our lungs and the atmosphere, is now just down by 1, okay, negative. And when pressure goes down, what happens to our volume?
Increases.
It wants to increase, exactly. And so we're increasing the volume, which acts as, suction or a vacuum, and it's forcing air into the lungs. Okay, very good. But if we're looking at forced inspiration, then it's going to change just a little bit more. Okay. Our intrapulmonary pressure is going to decrease by 1 more, 758. Okay. And so that is going to cause, okay, that is going to cause our lungs to decrease to 758. And it's just by that 1. And that's going to further decrease the pressure, which is going to further increase the volume inside our lungs, which is going to give us more air inside our lungs. Okay. And then that quiet expiration, it's going to push our lungs past the 760 to 1 by 1, and increasing that pressure even just by 1, because now inside our chest cavity, it's back to normal. And atmosphere is still 760. Even though it's just 1 millimeter of mercury, it is increasing the pressure just enough in order to decrease the volume. Okay. And so we're going to be pushing air out of our lungs. And then if we're forcing the expiration, it's going to increase that pressure inside the lungs by 1 more, as well as your chest cavity pressure by 1. Okay. And so that's going to further increase our pressure, which decreases the volume even more, pushing even more air out of the lungs. Okay. Okay. What I want to do is I want everybody to take a 5-minute break. Okay, before we go into kind of the physiology behind the signals in the brain to make you breathe, I want you to take a 5-minute break and just process that information, okay? So come back to me in at 12:34. Okay? Okay. If we all let that process and marinate in our brains, it's a lot of numbers, it's a lot of information. Okay. Just wanted to give you guys an opportunity to let that all sink in before we moved on to something else that's equally complicated. Yay. Airway's great. Okay. Okay. Um, any questions or comments before we move on? I just want to make sure that I'm not running over anybody. Delightful. Wonderful news. Okay. All right, let's talk more about the physiology behind how we breathe. Okay. So our breathing is mainly controlled by our medulla, okay, as well as our pons. All right. And so these are the top of your brain stem that connects to your cerebrum. All right. And back here is your cerebellum. Okay. Your pons is your big giant, I don't even know what to call that. Flab, protuberance. Anyways, it's the big one on top. And your medulla is the small one on the bottom. Okay. And then it goes into your spinal cord. All right. Some places you want to know. I'm actually going to start from the bottom and go to the top. Okay. So in your medulla, you have two groups. There's your dorsal respiratory group and there's your ventral respiratory group. Okay. Your dorsal respiratory group is the main regulation for inspiration. Okay. This is the one that sends the excitatory cells to your lungs through your synapse and tells you to inhale. Okay. Your ventral respiratory group also has motor control over inspiration as well as expiration, but it mainly regulates your forced expiration. Okay. So on a normal day, our dorsal respiratory group is mainly in charge of inspiration. Okay. And then, of course, with quiet expiration, nothing's in charge of quiet expiration because we're just letting everything return back to normal. Okay. What manages those is your apneustic center. Okay. And that is at the bottom of your pons. All right. And your apneustic center is what stimulates your respiratory groups. Okay. With excitatory cells. Okay. And so it's sending signals to these based off of chemoreceptors, which we'll talk about in a bit. Based off of chemoreceptors, it's going to say, oh, we need to inhale. And so I'm going to send some excitatory cells to stimulate the dorsal respiratory group so that the body knows we need to expand the thoracic cavity so we can inhale, we need more oxygen, or we need to slough off some carbon dioxide. Okay, so our apneustic center is what stimulates these groups. Our pneumotaxic center sits at the top of our pons, and this controls the rate and depth of breathing by inhibiting the apneustic center. Okay, so our apneustic center is just excitatory happy. It's just like, I'm just glad to be here so that we can be inhaling and exhaling like there's no tomorrow. Okay. Mainly inhaling like there's no tomorrow. Okay. But our pneumotaxic center kind of regulates our apneustic center. It also receives signals from chemoreceptors and stretch receptors and all different kinds of receptors in our body to say, okay, we need to breathe faster. So I'm going to lay off a bit and let the apneustic center do its thing. It can excite all the dorsal respiratory groups. Okay. Or, hey, we need to slow down. And so the pneumotaxic center is going to come in and inhibit the apneustic center so that the apneustic center is not stimulating the dorsal respiratory group or ventral respiratory group. Okay. It can also control the depth of breathing by saying, I'm going to lay off because I want us to breathe in more deeply. Whereas if your pneumotaxic center wants less depth, okay, more shallow breathing, then it's going to, oh, I think I have that backwards. If it wants more shallow breathing, then it's going to lay off, because what that's going to do is it's going to let the apneustic center stimulate the dorsal respiratory group as much as it wants. And if you breathe faster, then you naturally breathe more shallow, okay? But if you breathe slower, you typically have more time to breathe more deeply, okay? So our pneumotaxic center only sends inhibitory cells. It only stops the apneustic center or doesn't stop the apneustic center, okay? Our apneustic center only starts the respiratory groups, okay? And we're mainly stimulating the dorsal respiratory group because that is what regulates inspiration, that regulates inhalation. That's the same thing. Or if we need forced expiration or a little bit of extra help, then we'll stimulate our ventral respiratory group. Okay. Any questions about that? The complex is called pre-Botzinger complex. That is what generates a respiratory rhythm. And that happens in your dorsal and your ventral respiratory group, pre-Botzinger complex. That's what generates the rhythm. Okay. Oh, every time. No. Okay. So our body has said, hey, we have too much carbon dioxide in the body. So we need to do something about that. So our chemoreceptors, which have sensed that there's too much carbon dioxide in the blood, has sent a signal to the brain, to the pons. And so now we want to breathe more quickly in order to slough off more carbon dioxide and take in more oxygen. So our pneumotaxic center is going to lay off a little bit, let apneustic center do its thing. And our medulla is going to send signals through our nerves, our cervical and our thoracic nerves, to the muscles of the chest wall and the diaphragm, okay? So our cervical spine is what controls the phrenic nerve. It innervates the diaphragm, okay? And you'll hear C3, C4, C5 keeps the diaphragm alive. And the reason why we say that is because if you have somebody who has any kind of injury to the spine or the head, that is something you want to be aware of, because if there is any damage to C3, C4, C5, that is going to impede their ability to breathe. Okay. Anything underneath that just becomes disabled because it's cut off from the brain. So at C3, C4, C5, your patient no longer has the ability to breathe for themselves. All right. Now, once we get down to the thoracic spine, our T1 through T8 innervates or is our intercostal nerve, and that innervates our intercostals. Okay. So if you have a spinal injury that's in the thoracic area, that's going to make it difficult to breathe, but it's not impossible. They still have innervation to their diaphragm, but they may have less signals going to their intercostal muscles, okay? All right. I want to make sure that I covered everything that needs to be covered there. Okay. Okay. So when talking about our chemoreceptors, oh, you know what? The other thing I wanted to mention is the Herring-Brewer response, I think is what it's called. Hang on. Yeah. Oh, reflex. So your Herring-Brewer reflex is a feedback loop that prevents overexpansion by terminating inspiration. Okay. So when you inhale, there's a point where you can't inhale anymore. And that's because there's a feedback loop happening inside your system called the Herring-Brewer response. That's, I'll write it out for you in a minute when I switch over to my iPad. But that Herring-Brewer reflex basically triggers your stretch receptors and says, okay, we have expanded to this point, and if we continue to expand, something's going to break, something's going to pop. And so we need to stop. All right. And that is the point where you cannot inhale anymore. And so those stretch receptors are sending signals here and saying, hey, stop inhaling. And that is when that is inhibited. Your pons, your pneumotaxic center inhibits your apneustic center. And now there's no more stimulation for inspiration. And so now we can relax the chest wall, we can relax the diaphragm, and then it pushes all of that air back out. Okay. So that's the Herring-Brewer reflex. The other thing I wanted to mention is apneustic breathing. Okay. This is a type of breathing that is not good. And it basically means that we have prolonged inspiration and very short expiration. And that usually means that something is malfunctioning up here in the pneumotaxic center. Okay. And so our apneustic center is basically going unchecked. And the only thing that's keeping yourself from constantly inhaling are your receptors, your stretch receptors that are responding to that Herring-Brewer reflex and saying, we cannot physically inhale anymore. We're going to pop. And your chemoreceptors that say, okay, that's too much oxygen, or okay, we need to get rid of some carbon dioxide. And that is all that is inhibiting your apneustic center. Otherwise, it is going to inhale and inhale and inhale. Okay. So those two things. All right. So in talking about our chemoreceptors, this brings up one of my favorite things ever, and that is the bicarbonate buffer system. Your body has many buffer systems in order to keep the pH balance where it needs to be so that you don't die. Because if you are anywhere too far out of 7.35 to 7.45 pH, you die. Too basic, die. Acidic, you die. Everybody dies. So homeostasis inside the body in general is between 7.35 and 7.45 on the pH scale. So we're just a little bit alkaline. We're just a little bit basic. Yeah, basic. Am I the only one that thinks that's funny? I think that that's funny. Anyways, okay. The bicarbonate buffer system is kind of, it is complicated. And so, but it explains so much, especially when we're talking about respiratory acidosis and alkalosis and metabolic acidosis and alkalosis. Okay. Has anybody just heard those words, seen them in passing? Yeah. Hopefully, if you've been watching your Master Your Medic videos, you've probably heard about this, at least in passing, and it felt like drinking out of a fire hose, probably. I know it was the first time I read about it, and I just could not sit still. I had to understand. Okay. So we're going to start right here, and then I'm going to end up switching over to my iPad screen to write stuff out so that you can kind of see how it works. Okay. So our body has a constant shifting in pH, okay? Because we are constantly putting things in our body that are either acidic or basic, either through ingestion, either we're eating or drinking something, or medication, or the atmosphere, whatever we're breathing in, whatever, anything that goes on our body. You can go to the pool and you're sitting in chlorine and that's being absorbed into your body. Okay. So you're experiencing things all day long for your entire life that are constantly shifting your body's pH level all over the place, or at least it's trying to. And the reason why those things aren't killing you is because of your bicarbonate buffer system. Okay. So, before I switch over to my iPad, we're going to talk about this here chemical equation. Okay. We're going to start here in the middle with our carbonic acid. Carbonic acid is a weak acid. Okay. And it is H made up of 2 hydrogen, 1 carbon, and 3 oxygen. Okay. You can break up your carbonic acid into hydrogen, a hydrogen ion, and your bicarbonate. Okay. Your bicarbonate is a weak base or alkaline. Okay. It's weak. Your hydrogen ion, your freestanding hydrogen ions are very strong acids, and your pH level is based on how many free roaming hydrogen ions are in your body. Okay. So more hydrogen ions means more acidic, which means lower pH score. Okay. Less hydrogen ions means less acid or more alkaline, and that is a higher pH scale or pH number. Okay. So our carbonic acid is a weak acid. Our hydrogen is a strong acid. Our bicarbonate is a weak base. And these can be added together to create carbonic acid, or carbonic acid can be broken up to create a hydrogen ion and bicarbonate. Okay. The same can be said over here. Your carbonic acid can also be broken up into water and carbon dioxide. Or water and carbon dioxide can become combined to become carbonic acid. Okay. Water is neutral. It's neither alkaline or acidic. But your carbon dioxide is acidic. Okay. And so your body doesn't want it in the system. Okay. All right. So I'm going to stop sharing this real quick and I'm going to share my other one. All right. See here. We're getting high tech. Give me just a sec. Alrighty here. Alrighty. You guys see? Can I get rid of this? You guys see my screen? Fantastic news. Okay. So if I have, this is going to have to move somewhere else. Oh, fantastic. Okay. So if I have my pH scale over here, okay. And up here is more alkalytic, and down here is more acidic, and in the middle is our neutral area, then we as human beings want to stay about right here, okay? And anything more or less is going to kill us, all right? So if we look at our chemical equation, okay, then we're going to see a couple different things, okay? So what did I say controls our pH level?
Hydrogen.
Hydrogen, okay? Your freestanding hydrogen ions. This is what controls that. So alkalytic is less hydrogen ions and acidic is more hydrogen ions, okay? And remember that your pH scale goes from 0 to 14, all right? So less hydrogen ions means higher pH number. More hydrogen ions means lower pH number, okay? All right, so let's take a look over on this side first, okay? This is metabolic, meaning it's happening inside the chemistry of our body, okay? What happens is, say I have had 6 gallons of orange juice and my entire body is extremely acidic, okay? Very, very acidic, which means I have lots of freestanding hydrogen ions in my body, okay? Because of my 6 gallons of orange juice that I just drank. What my bicarbonate buffer system is going to do is it's going to say, oh, we have all these freestanding hydrogen ions. We are going to combine with those. And even though combining our bicarbonate and our hydrogen is still going to create an acid, okay, it's going to create our carbonic acid. What is our carbonic acid? Is it weak or is it strong?
So weak.
So weak. It is like so weak. All right. It is a weak acid. It is much, much weaker than hydrogen, and it's decreasing the number of freestanding hydrogen ions, which is then going to increase our pH. Okay. Because our body can handle a carbonic acid much better than it can handle too many hydrogen ions. Okay. Now the same can be said of the opposite. Say, this is completely unreasonable, but say I drank 6 gallons of soap. Now my body is very basic. Okay. It's very alkalytic. And so now my body's going to say, oh, hey, we've got all of this carbonic acid, and carbonic acid is weak AF. What can we do to make our body more acidic? Because right now we're basic, okay? What are we going to do? We're going to bust up our carbonic acid, and we are going to create our bicarbonate and more freestanding hydrogen ions in order to increase the acidity inside our body, okay? This is metabolic, okay? This is metabolic alkalosis versus metabolic acidosis, okay? So if we have metabolic acidosis, what does that mean? What does it mean about
Too much acid, right?
too much acid? And
Too
how
much
do we
CO2.
translate that in our bicarbonate equation? We're not even looking over here yet. Ignore over there. We're looking this way. Okay. What does that mean? If it's too much acid, what is there too much of?
Hydrogen.
Too much hydrogen. Okay. So metabolic acidosis means too much hydrogen, which means our pH level is too low. Okay. And what our body is going to try and do is it's either going to try and combine with our bicarbonate to create a weaker acid and in order to increase our pH level to take us out of acidosis and make things metabolically neutral. or it's going to use our respiratory system to help equalize things. Okay. And we'll talk about that in a second. Metabolic alkalosis. What does that mean?
Too basic.
You're too basic. All right. You're too basic. Not enough freestanding hydrogen ions. Your pH number is too high. Okay. And so in that case, we're going to bust up our carbonic acid in order to make more freestanding hydrogen ions, or we're going to engage our respiratory system to help us out. Okay. So, like I said, there are lots of different buffer systems in our body in order to equalize, neutralize our pH score, our pH balance to maintain that 7.35 to 7.45. One is our bicarbonate buffer system, which is what we just talked about. The other is our respiratory buffer system. Okay, you also have like a cardiac buffer system and a protein buffer system and a renal buffer system, all the buffer systems. Okay, give me 2 seconds. Okay. So let's talk about the respiratory buffer system over here. Okay. So knowing what we know about our metabolic, let's try and break down our respiratory side of things. Okay. So I want to jump right into respiratory acidosis. What do you think that means? What do we have too much of in our body?
Carbon dioxide.
Too much carbon dioxide. Okay. Too much carbon dioxide. I'm going to put it under here. Okay. Too much carbon dioxide, which means our pH is too low. Okay. But what if we're in respiratory alkalosis? What does that mean? What do we have not enough of?
CO2.
Fantastic. You're doing great. Not enough CO2, and our pH score is too high. Okay. Now, if you were like me and it was like it was more than 3 years ago, but a few years ago when I realized it's actually healthy to have some CO2 in your body, I found that to be quite the shock because I grew up and I was just like, no, CO2 is muy mal. It's very bad for you. You want 0 CO2 in your body. Incorrect. You do not want 0 CO2 in your body. You want some CO2 in your body because it balances out your body's pH. That is one of the reasons why it's there. Okay. And so it's okay to have some CO2 in our body. It is normal for us to have some CO2 in our body. It is necessary to have some CO2 in our body. Okay. It is when we have too much or not enough that it becomes a problem. And it's the same with our freestanding hydrogen ions, right? And so our body becomes, finds itself in respiratory acidosis. It's acidic when there's too much CO2 in our body. Now, what can cause our body to have too much CO2?
Hyperventilation.
Hyperventilation or hypoventilation? What does hyperventilation do?
It'd be hypo because if we're hyper, we're breathing. Wait, no. Yeah.
Could be either.
See, this
So
is where it gets
it'd be
people.
hypo, right?
Yeah, this is where it gets people. So it is hypoventilation. So I think Gage threw it on there. Oh, hi. Sorry, guys. There's like I said, I forget that the chat happens ever. So everybody's great. You're all doing fantastic. But yes, Gage, not breathing. And here's the reason why. Is because if you are not breathing, say your Your respiratory rate is 6, okay? There is little gas exchange happening, okay? And in order, when we are breathing, okay, what are we breathing in? Hopefully.
Oxygen.
We're breathing in oxygen. So if we inhale, we get more oxygen. And what that does is oxygen then displaces the CO2 on our hemoglobin in our blood, okay? But if we're not breathing enough, then there is not enough oxygen. And if we don't inhale, we can't exhale, okay? So not only is there not enough oxygen to displace the carbon dioxide on our hemoglobin, but there is nothing to push the air out of our body, okay? The control is inhalation, all right? The only thing that can get us to take air out of our body is forced expiration. And even then, that is very hard to do if there is no gas to replace the carbon dioxide, okay? And so consequently, if you're not breathing enough, your CO2 has nowhere to go, and so it stays in your body, okay? And it creates a more acidic environment, all right? And so you can become acidic, you can have respiratory acidosis if you are not breathing at all, or you are not breathing well enough to get the oxygen in your body and the carbon dioxide out of your body, okay? So respiratory acidosis can come from hypoventilation, all right? Okay, now what about respiratory alkalosis? There's not enough CO2 in our body. If we take the opposite, hyperventilation, what's happening? What is happening when we're hyperventilating?
We're breathing off our CO2 at a more rapid level.
Yeah. So Gage, yeah, you're partially correct. And yeah, yes, awesome. You guys are so so smart. I'm so proud. You're breathing so fast that all the oxygen is getting in your system. But there's no time for the oxygen to perfuse your tissues because you're breathing so fast, it's all happening too fast, and the exchange can't happen fast enough. Okay. So it's happening inside your alveoli, but it's not necessarily happening in your cells. Okay. And we need that to happen in our cells. Okay. So we have too much oxygen in our body that is displacing too much CO2. And so now we're sloughing off too much CO2 and things have become alkalotic. Okay. And so hyperventilating is going to create respiratory alkalosis. All right. Now, what our body will do, here's one of the tough things though, is that it's hard for us in a pre-hospital setting to see where they are on the pH scale. So is someone in respiratory acidosis and they're hyperventilating because they're trying to slough off more CO2? Or are they sloughing off too much CO2 because they're hyperventilating? Which came first, the chicken or the egg? Okay. Your body is going to use these buffer systems in order to reach that homeostasis again. That is why the buffer systems are there. Okay. Any questions so far? Amazing. Fantastic news. Okay. We're going to jump back on my presentation. If I can figure out how to stop doing this. Okay. 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 So what helps us know what's happening inside the body is our airway assessment tools. Okay. So one that we all mostly have access to is our pulse oximetry. Okay. You can see them in just the devices that just clip on your finger, and it's just that it's not attached to a monitor or anything. A lot of people have those. Or for us, where we have monitors, we'll have these right here. Okay. These devices. Hello. Okay. These devices right here. And what they do is they send an infrared light through your finger, because that's where the probe goes, through your finger, and it's specifically looking at pulsating vessels. Okay. And pulsating vessels are our arteries. Okay. Because they are closer to the pump. They're pushing blood through the system in order to oxygenate things. And so these machines are specifically calibrated to find the pulsating vessels so that it's not measuring the oxygen off of blood in the veins, which is deoxygenated. And instead it's measuring the oxygen levels on your arterial red blood cells. Okay. Yeah. And I say oxygen and I should just be saying gas molecules, because there's a point where someone is not perfusing very well. They're not getting oxygen to their tissues, but their pulse ox may say 100%. And those are the situations if someone is suffering from carbon monoxide poisoning, because carbon monoxide has a higher proclivity for to attach to hemoglobin than oxygen does. And so carbon monoxide will push oxygen molecules off of the hemoglobin and replace it. And it is very hard to push it back off. In which case those patients need hyperbaric chambers. So, okay, but your pulse oximeter doesn't know the difference between oxygen and carbon monoxide. It only sees that a gas molecule is attached to the hemoglobin in your pulsating vessels. Okay, so that's really important to remember. Another device is Peak. Okay, that's this device right here. This is to kind of judge the bronchoconstriction versus dilation, as well as any responses to breathing treatments. You'll find these in like doctors' offices or hospitals. We don't really see these in pre-hospital. Arterial blood gas, or ABGs, that's this right here. I mean, it's the best I could come up with. They take a sample from your arterial blood flow, and then they put it in a machine, and that machine offers quantitative or comprehensive information about your respiratory system, about what gas exchange is happening, how much is there, how much is not there. And it's really, really awesome. And you see that in your hospitals. Okay. The last one is end tidal CO2. Okay, this detects CO2 in exhaled air, and this can be you can use a few different devices. Okay, you've got colorimetric, which is this right here, this little gauge with a purple piece of paper in it. This provides qualitative information through color changing paper. It comes as purple, and then when CO2 is blown through it, it will change colors depending on how much CO2 has been exhaled, okay? Now, the thing about these is they're kind of a one-time use. They're like for checking an advanced airway. They're also really sensitive to temperature, or if someone has had carbonated beverages that are still in their digestive system, that can change what this looks like, as well as any kind of contaminant that gets inside of it that can skew the reading. And so they are helpful, but they're not the best. Okay. A capnometer, that's what this guy is. This provides some quantitative info through exhalation. So you get an end tidal CO2 number right here as well of a respiratory rate. And their tidal volume as well. Okay. Capnography, I'm a little biased, but this is the best. It's also the most preferred to confirm advanced airway placement is through your capnography. Capnography provides graphic info through waveform patterns to give you quantitative info in real time. And so what's nice about these is that it's more than just a one-time thing, okay? This will constantly be reassessing your end tidal CO2 score as your patient is breathing or as you're breathing for your patient. This right here is like a nasal cannula. And so this obviously goes into their nares. And then for adults, there's this pretty big little tab thing that goes over their lips. And any exhaled air, it is measured here, and it goes through this one side that goes to your monitor. It hooks up to your monitor with this piece here. Okay. And the nice thing is on the other side, you have access to oxygen. So if they need oxygen, they can still get it through a nasal cannula, but you're still able to get an accurate reading of their end tidal CO2 from this other side. Okay. So that's nice, but they also make adapters for like a BVM. Okay, so rather than it having this piece right here, it has a little tube that just connects to your BVM in between your BVM mask and the actual BVM. And then it reads the end tidal CO2 from exhaled air as you're bagging a patient. So that's pretty cool. Anyways, a little bit more on your end tidal. End tidal carbon dioxide, okay? This is the measurement of CO2 taken at the end reading of tidal volume. So this is what your capnography is going to look like. This is the waveform. Your oxygen, your pulse oximetry is going to be more of like a triangle or a pyramid, whereas this is more of a square, a funky looking square, okay? And your end tidal is also opposite from your pulse oximetry, where your pulse oximetry is going up with an inhalation and down with exhalation. This right here is going up with your expiration and down with your inhalation, okay? So respiratory baseline, this is when we are at rest, when all of the pressures in the lungs, outside the lungs, in the atmosphere are all where, you know, everything is like kind of equalized, okay? And then this is excuse me, that's incorrect. This is the top of your inhalation, okay? So you've just inhaled to the point you're able to, or just the point you need to. So you've just right there before you exhale, that is where this respiratory baseline is, okay? And then as soon as you start to exhale, this is going to go up. And then as you reach at rest, it's going to slow down, start to plateau. And then right here, when you've reached the end of exhalation and are about to inhale, this is the end tidal of your CO2, okay? And it's at this point that reading is taken. That's the maximum amount of CO2 that has been exhaled. And now you're inhaling, which is obviously going to make that count 0, because while you inhale, you're not exhaling any CO2, right? So if we're looking at our score for end tidal or our measuring or reading, normal for a person should be between 35 and 45 millimeters of mercury. That is normal. So if we're considering our bicarbonate and respiratory buffer systems, what would the end tidal CO2 be in respiratory alkalosis? What would that number be? What do you guys think?
Above 45
Would it be
millimeters.
above or below? This is also kind of a tricky question. This is where people start to get stuck. Because you think, well, if you're breathing more end tidal, that should mean that you have less in your body, right? And so shouldn't the number be higher and that means there's less CO2 in your body? No, the answer is no. Okay. The lower the number, the less CO2 in your body. The higher the number, the more CO2 is in your body. Okay. And the reason why is because this is measured in millimeters of mercury. This is measuring pressure. But if we look at our partial pressure, this is the amount of pressure in millimeters of mercury it takes for a gas to diffuse across the barrier between alveolus and vessel. Okay, so that membrane that connects the alveoli and the blood vessel, that is where gas exchange happens through diffusion. Okay, and so it requires a certain amount of pressure to push a gas molecule past that membrane. Okay, and normal gas exchange for your CO2 takes about 35 to 45 millimeters of mercury. Now, the nice thing about partial pressure is that it is directly correlated to how much gas is being exchanged, okay? Or is in the system, okay? So if your body requires higher pressure, then there is more in your system, okay? And it's gross, but it's like needing to pee. If you go a really long time without peeing, then your bladder is full, okay? And then when you actually pee, man, it shoots out of you like a rocket. There's high pressure, there is a lot of pee, and there's high pressure because we are trying to get all of that out of our system, okay? And so consequently, there's more and requires more pressure to get it out, okay? So if we look at our end tidal, if it's at 60 millimeters of mercury, it means it's requiring higher pressure to get more of it out. So we have a higher end tidal at 60 millimeters of mercury because there is more CO2 in your body that needs to get out, okay? So that is indicating a lot of carbon dioxide is trapped inside the body, okay, that your body is trying to get rid of, but can't. All right. And the same is said of less. If you have an end tidal of 20, then there's less pressure required to get less carbon dioxide out of your body because there's just not enough. Okay. Does that make sense? It's kind of a confusing number, but if you just remember that that number is directly correlated to how much is actually in your body, that is what the CO2, that is what end tidal is measuring, is how much pressure it takes to get the CO2 out of your body. And if there's more pressure, it means there's more CO2 in the body. And if there's less pressure, there's not enough CO2 in the body. And the ideal score is between 35 and 45. Okay. Any questions? Amazing. Fantastic news. Cool. If there are, remember, you can just shout it out. Oh, I'm actually gonna chat. Hang on, wait, I'm gonna check this. Oh, I will absolutely say that again about the end tidal number. Did that just happen? Oh no, that was like 3 minutes ago. Sorry, Gage. Yeah, so your end tidal number, we want it to be between 35 and 45 millimeters of mercury, okay? And if it's higher, it means that more pressure is required to push more CO2 out of your body, okay? So at 60 millimeters of mercury, there's more pressure required to push the CO2 out because there's more CO2 in your body that needs to be pushed out, okay? If it's 20, then there's less pressure to get the CO2 out of your body because there's less CO2 in your body. There's just not much to move from one place to another, okay? Did that help? Maybe, maybe not. I hope so.
I had a
Oh.
quick question also.
Yeah, go for it.
Is there anything we can do as providers to change this? I can see it being helpful information for like a vented patient, I guess, knowing how to adjust their vent, but is there anything we can do to get more CO2 out and give more CO2 in?
Sure. So if they have a high end tidal, that means there's too much CO2 in their body. So what do we want to put in their body to replace it?
Oxygen.
Oxygen. You can give them oxygen. You can put them on a non-rebreather or a nasal cannula, depending on how much is in their system. Now, someone maybe has a high SpO2. There is really not any damage that we can do to someone in the pre-hospital setting with oxygen. You can have oxygen toxicity, but that's over a long period of time if you're giving somebody too much oxygen. Now, we're not going to throw every patient on 15 liters of oxygen. I know that is just heresy. You learned everyone gets 15 liters of oxygen on a non-rebreather in your basic class, but that is not the case. We want to make sure that we're titrating to the need. But if somebody has a high end tidal, we can put them on some oxygen, hopefully in order to displace some of that CO2 to help them exhale it out of their system. Okay. If they have low end tidal, really all we can do in that situation is try and coach them on their breathing, because it's likely that it's low because they're hyperventilating. So you'll see that in patients with asthma or patients with having panic attacks or anxiety attacks or whoever they're hyperventilating for whatever reason, and coaching them on their breathing can be really, really effective. Box breathing. Hopefully everybody's heard of the box breathing method, where you inhale for 4 seconds, hold for 4 seconds, exhale for 4 seconds, hold for 4 seconds. Okay. That will help regulate someone's breathing. So that's something that you can do in order to help increase their CO2, is just because they're sloughing so much of it off when they're hyperventilating. That coaching their breathing can help a lot.
I never heard of that method until just now.
Really?
That's the first time I've heard that. Yeah.
Oh man, yeah, they coach that, especially I know in like firefighter training. I heard that they would teach firefighters that, because if you're hyperventilating, you burn through so much of your oxygen that's in your tank. And so you go through that tank a lot faster than you would if your breathing were more controlled. And I remember that being a really big deal to me. If anybody's seen the Chris Hemsworth, oh no, now I don't remember what it's called. Limitless? I can't remember, but it's like 6 episodes where he goes through various challenges. And one of them was learning how to decrease the cortisol in his system. So that's like the stress hormone. And one of the things they did is they put him through fire training. And they hooked him up to an oxygen tank. They put him in a burning building, and they monitored his breathing that way. And I remember it hitting me so hard because he couldn't finish because he burned through all of his oxygen because he couldn't control his breathing. And so half of the building went unsearched because of that. And I remember thinking, wow, what a horrible thing if somebody were up on the second floor of the building who could have been saved and wasn't because I couldn't control my breathing, you know? And so learning to be able to control your breathing is a big deal. And one of the things that they teach, that they taught him in that situation and they teach in general, is box breathing, because it almost, vaigles your way down to controlling your depth and the rate of your breathing. It's basically teaching your pons and your medulla to reset. It's like, we do not need to let our apneustic center run wild. We need to be engaging our inhibitory cells. We need to slow down. Okay. So yeah, box breathing. Inhale for 4 seconds, hold for 4 seconds, exhale for 4 seconds, hold for 4 seconds. And if you just do that, then you can sustain that for a while without somebody getting lightheaded, and that'll help slow their breathing. So
Can I add something interesting I've heard?
yeah, please.
Well, first off, I personally use box breathing when I'm feeling overwhelmed, and it works for me. I've seen it work pretty well, I guess. But I heard something interesting as far as people were saying it's kind of a psychological trick. It was a paramedic I was talking to said that sometimes if you see someone hyperventilating, he'll give them a non-rebreather and tell them that they're on oxygen. But really, he's just putting the mask on, and just it's almost like you're giving them a paper bag. You're like kind of tricking them into calming their own breathing, and they're like, oh yeah, I'm feeling better. That oxygen's working when there's really no oxygen flowing.
Yeah,
So I found that pretty interesting when he told me that.
that is
So
interesting.
I'm not sure if that applies in all situations, but I thought it was pretty cool.
Well, I mean, it definitely applies in the respiratory acidosis versus alkalosis. If they're hyperventilating, then they're sloughing off CO2, and you put a non-rebreather on their face, then they're basically recycling the CO2 that they're sloughing off and putting it back in their
Mhm.
system. That's going to increase their end tidal. But obviously that's something you have to monitor, because you're also not replacing their oxygen. So,
Right. Yeah.
But yeah, that's what makes non-rebreathers so effective, is it kind of slows that process. It's not just giving them a ton of oxygen all at one time. It's helping that process a lot more. I was going to say something. What was it? I can't remember. It left my brain. Yeah, so box breathing is really great. Really great for us too, especially if we're going on a high stress situation, a high stress call. If you just give yourself a minute to box breathe, that will help you as well. Because if we're breathing too fast, it's kind of like, I don't know if anybody has seen the video of it. It's a ski lift that just, I think the motor broke, and so the ski lift was just going wild. And people are on the lift, and when it gets to the point where they're trying to get off, it's going so fast that people don't have time to get off, and they basically have to jump and hope that it's fine. You think about that. If your blood is pumping so fast and you're breathing so fast, you may be inhaling oxygen, but there is not enough time to exchange the oxygen and have it perfuse to your tissues, which is a big deal when talking about your brain. Your brain really needs oxygen. I mean, your whole body really needs oxygen, but especially your brain. And that's why when you have people who are hyperventilating, they get really lightheaded and then they pass out, because their body is just like, okay, hard reset. You need to calm down. And when somebody passes out, they're not hyperventilating anymore. It's the same thing. If somebody's not breathing, you're going to pass out, because now you're going to go back to normal breathing so that you can get oxygen in your system. That's your body's response to doing that. Okay. Coo. All right. Speaking of which, let's see, where are we at? I'm going for an hour. We're almost done with this right here. You know what? Go ahead and take a 6-minute break. Come back at 13:40. And then we'll finish this up and move into respiratory emergencies, okay? So 13:40. All right. We all back? Incredible. How we all doing? We doing okay?
Hanging in there.
Hanging in there. It's almost over. At least the informative part is almost done. We've got like 2 more slides left before we move on to our respiratory emergencies. So hopefully that'll be a little bit easier. Hi. You guys want to meet my dog?
Of course.
That's Dakota. Hi, baby. Anyways.
Dakota.
Oh, look. Look. Everybody says hi. Anyways, she's tired of being stuck up here. No, she's not. She loves me so much. Okay. Alrighty. Let's talk about hypoxia. Okay, hypoxia is the lack of oxygen in the cells and tissues of the body. And this is an immediate emergency. We need to make sure that we are fixing hypoxia, because if the body is not getting oxygen, if the body is not getting is not perfusing, then it doesn't matter what else we do, that it's not gonna matter. Yeah, it's not gonna matter. If we don't have oxygen, then basically, if you don't have oxygen and you don't have blood moving around your body, then it's nothing else is gonna matter. Okay. I want to chat for a second about hypoxic versus hypocapnic drive. Hypoxic drive is your body's chemoreceptors responding to, oh, there's not enough oxygen in the body, we need to breathe more. Hypocapnic drive is, oh, there's too much CO2 in the body, we need to breathe more. Sounds like the same thing, but hypocapnic drive is what normal people do. It is the normal healthy body response, and it is much stronger and faster than a hypoxic drive. Hypoxic drive is like the backup if hypocapnic drive doesn't is hindered by any, oh man, I spelled it wrong. Dang it. If it's hindered for any reason, okay? You'll find hypoxic drive in your COPD patients. That is what triggers their ability to breathe. And so that's usually why they're having a bit of a more difficult time. Okay. Your early signs and symptoms of hypoxia are just restlessness and irritability, apprehension. You're going to see tachycardia and you're going to see anxiety. Okay. Your body, if you remember from one of those very first slides we looked at, when your body is going without enough oxygen, for, even under a minute, you're gonna start wanting to move around. Your body is gonna start grasping at straws, essentially. It's gonna find any way that it possibly can in order to get more oxygen into the system. Okay. And then if oxygen is still not finding its way into the system, you're going to see late signs and symptoms. Okay. And that's going to be an altered mental status because we're not getting oxygen to the brain. So you can't think very clearly. You're confused. Your pulse is going to weaken because you're going to start shunting what little oxygen there is in the system. You're going to start pushing to the parts of your body that are more necessary at keeping you alive, like your kidneys, and then ultimately your brain, your heart, your lungs. So you're not going to be feeling strong pulses radially or in your feet or anything like that. It's just going to slowly shunt away. And then cyanosis. I don't know if any of you thought the way that I used to, which is, oh, they're blue, oh, hypoxia. I mean, yeah, but we want to fix it before they start to turn blue, because turning blue indicates a lot of shunting has happened. Now there's no oxygen perfusing the limbs. There's no oxygen perfusing things like the lips, around the mouth, and then depending on what part of them is blue, is it the whole entire body? Is it just the limbs? Can tell you about how hypoxic they are or how long they've been without oxygen. Okay. So we want to make sure that we are noticing the early signs and symptoms before they start to turn blue, so that we can fix it so that they don't turn blue. Okay. So that restlessness, irritability, apprehension, anxiety, and that tachycardia can indicate. Also, pulse oximetry. If their oxygen level is below 94%, they're going to start feeling a little uncomfortable. Okay. If it's under 90%, they're going to start feeling a lot uncomfortable. And then it gets worse as it gets lower. Okay. We want to make sure that we're giving them enough oxygen to keep them between 94 and 98. Anyone know why we don't want to push it up to 100? What do you think?
The pulse oximeter could be off.
It could be. Yeah, for sure. What else? There are other reasons. There's lots of reasons. Yeah. Peter says you got to leave room for CO2. If you start pushing too much oxygen into their system, you're going to start sloughing off CO2. And so if you're like, oh, fantastic, their pulse oximetry is at 100%, and you're not monitoring their end tidal CO2, you could be causing them to get into respiratory alkalosis, right? And if it's long-term oxygen, then they can start suffering from oxygen toxicity, and that's a big problem. Yeah, and so our goal is to kind of be between 94 and 98%. It also, if they're at 100%, it's a little hard to titrate to 100%. So maybe 15 liters of oxygen is going to get them to 100%, but 10 liters of oxygen might get them to 100%. Maybe even 5 liters of oxygen can get them to 100%. So you may be giving them a whole lot more oxygen than they actually need, right? But if we're aiming for between 94 and 98%, it's a lot easier to titrate your oxygen, excuse me, your oxygen to what your patient is actually needing. Okay.
And if we have a COPD patient, that number can be different, right? Based off their kind of normal levels, like it can be lower than what we expect. Is that right?
So yeah, with your COPD patients, yeah, I'm really glad you brought that up. With your COPD patients, you're going to be aiming for about 90 to 94. Because usually with more oxygen, it's more difficult for them to breathe. And it has to do with that hypoxic drive and the fact that their hypocapnic drive isn't activated. So yeah, COPD patients, it's usually more comfortable for them to maintain oxygen between 90 and 94. If they are experiencing more serious symptoms, then it's not the end of the world. If they're between 94 and 98%, it's really not the end of the world. They need oxygen more than they need to be between 90 and 94%. Okay. Okay. Ventilation perfusion ratio. This is also called VQ matching, VQ coupling, back VQ mismatch, things like that. V obviously stands for ventilation. Q stands for perfusion because Q is the beginning of a French word that means quantity. Also, quantity starts with a Q. I learned that from a video that I watched last night, so that was exciting. But your ventilation perfusion ratio has to do with your alveoli and the vasculature attached to your alveoli, okay? This has to do with your gas exchange. So if we look here to our left, we can see my very artistic representation of an alveoli that is clear and it is behaving normally. We have my very artistic representation of a blood vessel that's connected to it with blood flowing from left to right, because that's anatomically correct. Anyways, so our alveoli is clear, our blood vessel is clear, and there is equal ventilation to perfusion ratio, okay? So what ventilation is referring to is the gas movement in and out of your alveoli, okay? So oxygen that comes in and gas that comes and CO2 that comes out, okay? That is your that is your ventilation. Your perfusion is referring to the movement of blood in your vessels, okay? And the gas exchange that's happening between the alveoli and the vessels, okay? So if you look at this, we're going to call these oxygen, okay? We have 3 oxygen molecules that are coming into this alveoli. And we look at that, we have 3 red blood cells that need oxygen. Amazing. That's not exactly correct, but bear with me, okay? We have 3 to 3. Okay, the ventilation perfusion ratio is equal, and this is wonderful news. We're so happy about how equal it is, and we're just, all the OCD inside our alveoli are so happy, okay? Now, what happens if there's a blockage in our alveoli? Okay, for whatever reason, there's a buildup of something, or there's damage to the alveoli. And so now only 1 oxygen molecule can make it in. But now there's 3 cells that need oxygen and need to slough off CO2. Well, how many cells can benefit from this 1 oxygen? All 3? No.
Only 1?
Only 1, right? There's only so much there's only so much, or there's only so much room for oxygen, and there's only so much oxygen for each of your cells, okay? And so, and then if we look over here, we have a lot of oxygen coming in, but we have a constricted blood vessel. So we have lots of oxygen, but only so much room for the oxygen, okay? The oxygen that makes it onto this red blood cell is going to attach and it's going to exchange with the CO2, but the oxygen that's not used is now going to go back out and find somewhere else to go, okay? Because there's nowhere for it to be, okay? So in this situation, we have a good VQ ratio. In this situation, we have a low VQ ratio, okay? There's less ventilation than there is perfusion. And in this situation, we have a high VQ ratio. There's lots of ventilation and not very much perfusion, okay? Now, if that was confusing to you, I like to think of the end of a Pink concert. I am a Pink fan, and I got to go to a Pink concert last year. And I remember when we finished the concert, there's tons and tons and tons of people. We filled the Diamondback Stadium in Arizona. It was so much fun. There were tons of people. And when the concert ended, we all left, right? All at the same time. There's tons of us. Now, a lot of the people don't live in Metro Phoenix, and so they needed rides to get home. Now, if that's their own car, or there were these people with like little buggies, like bicycle buggies that they were toting people around, or like Lyft and Uber, there were lots of resources to get people from the stadium to their homes, okay? But when you look at it from the perspective of it being equal, It was, I'm teaching a class. What? They want to see you? Fantastic. Sorry, that was my boss. So if you have a ton of people who are trying to get home, there's just really no way for you to have enough buses or enough vehicles to get them home, right? And so if we look at this, there's a ton of oxygen that's trying to make its way onto red blood cells, the hemoglobin. It's gonna bottleneck, okay? And the oxygen is gonna go somewhere else, just like the people are gonna go somewhere else to find other way to go home. Okay. The opposite is also true. Anyone who comes to any one of my concerts, there's like 10 people. And then maybe there's like tons of Ubers or Lyfts or people who are trying to figure out how to make money for the night. And they're like, oh, what a great idea. We're going to go outside Morgan's super amazing concert and we're going to sit there and we're going to wait. We're going to take the tons of people that we expect that are going to be there. And then there was only 10 people. Well, now there's tons of vehicles and not enough people to go home. Okay. And so that's what we find when there's very little oxygen making it into an alveoli, but a lot of perfusion. Okay. Now, what happens is that when there's not very much oxygen coming in, this is a VQ mismatch, okay? Not enough ventilation, too much perfusion, okay? And that VQ mismatch, our body is naturally going to try and fix it, okay? And they do that by, okay, well, we have too many vehicles and not enough people to take them. So we're going to constrict this blood vessel so that we'll have less vehicles that matches the number of people to take them, okay? We will constrict the blood vessel so that there is less red blood cells, less hemoglobin going to that location. So it matches up with the amount of oxygen that's making it into this alveoli so that we're not overwhelming anything, okay? And the same is to be said of when there's a lot of oxygen and the body is going to dilate the vessel in order to increase blood flow to get more red blood cells, more hemoglobin for gas exchange, okay? So our body is going to compensate. Either we're going to increase vasodilation or vasoconstriction, or we are going to increase bronchodilation and bronchoconstriction. Now, where have we heard these words? Epi, hopefully, epi and albuterol. Those are our bronchodilators and our vasoconstrictors, okay? And that is because our body is trying to, if we are vasodilating, okay, we have really big vessels and lots of movement, but we're bronchoconstricting and not enough airflow is going through. This is the problem we are reaching, okay? And our body's trying to compensate by increasing our ventilations in order to push more oxygen in for the perfusion ratio, okay? And so our epi and our albuterol is going to help bronchodilate so that we can get more oxygen into the system, as well as vasoconstrict in order to lessen the perfusion so that we can now match our ventilation to perfusion ratio. Okay? Does that make sense? The biggest thing you have to understand with VQ ratio is that your body wants it to be equal. And if one is less than the other, it tries to compensate. And if it can't compensate, you're going to have problems. Okay? Awesome. I think that's the last. Yeah. Amazing. Airway management. Any questions about airway management in general? Phenomenal. Okay. Now let me Okay, so that was my super exciting PowerPoint presentation or Prezi presentation. Now you get JB Learning. Oh, that's airway management. That's not the one I wanted. This is the one I want. Respiratory emergencies. So the good news is that some of this is redundant, so we don't have to go through all of it. But we're going to take what we learned and we're going to apply it to pre-hospital emergencies, okay? Okay. Medical terminology is dyspnea. Another one is apnea. Dyspnea is difficulty breathing. Okay, this comes from DYS is difficulty. PNEA is breathing. Okay, so dyspnea, difficulty. Apnea is lack of breathing. Okay, or they're apneic. You've heard of sleep apnea. That's what that is. Okay. Dyspnea is a common complaint. It is also a symptom of many, many conditions. I feel like our body has like 6 ways of telling us that something's wrong, and it's up to us to try and figure out what combination of those telltale signs and what those telltale signs are trying to tell us. And sometimes it can be really hard because it's like, oh, dyspnea, cool. You narrowed it down to about 500,000 diagnoses. Okay. So we want to make sure that we're keeping medical problems in mind as we obtain history and perform an assessment. But as we talked about before, hypoxia is our number one. Okay, we want to make sure that we are supplying the body with enough oxygen in order to perfuse the tissues so that we don't cause ourselves worse problems. Okay. All right. We talked about upper airway. We know about that. The additional thing I want to add is the epiglottis sits just above your larynx, just below your oropharynx. And that epiglottis is a cartilaginous flap that basically flaps between your trachea to cover up or cover up your larynx, or to cover up your esophagus based off of if you're breathing or if you are eating and swallowing. Okay. And then gas exchange is happening in your lower airway. So we've talked about cardiac. We've talked about cardiology, the movement of blood. That was like last week or the week before, right? No, maybe. That might be next week. I can't remember. Anyways, but from your right ventricle, your body is pumping deoxygenated blood from your heart to your lungs through your pulmonary arteries. Okay. And it's pumping that through here to the capillaries that are over your alveoli. And that is where the gas exchange happens. And now oxygenated blood makes its way to the left atrium, then to the left ventricle, which is the big pump, and that pumps it to the rest of your body. Okay. From this page, biggest thing that you want to remember is that the anatomic differences between an adult's airway and a child's airway is a child's tongue is larger than an adult's tongue in ratio. So the ratio between tongue and the rest of your oral cavity is much larger in a child than it is in an adult. And so that can cause an obstructed airway. We just talked about this. We talked about inspiration and expiration and ventilation. If anybody ever has any questions or wants me to stop and clarify something, then let me know and I will do it. The medulla, diaphragm, thorax, air fills. Go to the apneutic center. We talked about that. Okay, so pathophysiology. We obviously know that adequate perfusion and gas exchange needs to happen in order for the body to receive nutrients and oxygen. Some complications that will interfere with that is any kind of obstruction. If it's an upper airway obstruction, whether that's a foreign body airway or asthma, restricting the upper airway, that'll cause wheezing, or lower airway obstruction if there's anything happening inside the bronchioles or the alveoli. Any chest wall impairment, so anything that may be introducing air or fluid to the chest cavity, and then neurological control problems, okay? If anything is happening to the pons or the medulla, and those are our control centers, like swelling in the brain or head injury or neck injury, those things can impede that gas exchange, okay? So we chatted for a second about alveoli and how they're made up of 2 types of cells. Type 1 allows for better gas exchange, and type 2, they make new type 1 cells and they produce surfactant, okay? And surfactant is that lubricant. The alveoli function best when they're partially inflated. You can think about that like the lungs, where we don't have to inflate them the whole way in order to get a good breath in, okay? And so partially inflated, it's enough surface area in order for gas exchange to happen, but it's not over expanding them to their full capacity every single time, because that'll wear them out, okay? Surfactant reduces surface tension of the alveoli, and that makes it easier for them to expand, okay? People with chronic lung disease make a surplus of red blood cells, and that can make your blood thicker, and that can also make it more difficult to oxygenate enough of the red blood cells, okay? Cor pulmonale is right-sided heart failure because of chronic lung disease, okay? And that is if your lungs are, if they're stopped up or something's impeding that flow, then obviously that's going to backflow into your right ventricle through the pulmonary arteries into your right atrium. And so that's going to cause right-sided heart failure, okay? We talked about hypoxic drive and hypercapnic drive. We've talked about acidosis and alkalosis. Causes of hypoventilation, so not enough breathing, any impaired lung function, or impaired mechanics of breathing, neuromuscular apparatus impairment, or reduced respiratory drive, okay? Let's see. Hyperventilation we've talked about, and alkalosis. Atelectasis is when the alveoli basically kind of combusts, it just gets destroyed. And so that damages, obviously the alveoli is damaged, which makes it much more difficult for gas exchange to happen because there's less surface area for it to happen, okay? This can also cause obstructed air passages and blood clots, and your pleural space in between your lungs and your chest wall can fill with air or fluid, and that'll cause a pneumothorax, tension pneumothorax, or hemothorax, hemopneumothorax, hemotension pneumothorax. There's like a bunch of different words for it, but they all equal bad, okay? A patient with dyspnea may also report air hunger and chest tightness. So it just feels like they can't get enough air in order to supply their body. I know that for me, I will feel this a lot of times when I wake up from a nap because I'm fairly certain I don't breathe. And so if somebody has not been breathing for some time or is not getting enough oxygen, you can feel like, I know I'm breathing and I know that my lungs are expanding, and yet I just don't feel like it's enough, and I need more, okay? Dyspnea is a common complaint in patients with cardiopulmonary disease, and severe pain can cause a patient to experience rapid, shallow breathing without pulmonary dysfunction. That can be elevated respiratory rate can be a sign of pain. And nothing is wrong other than that's just a body's response to pain. Okay. Any kind of infections, especially within children, can affect all parts of the airway. Children are especially affected because of that ratio between, body and airway and tongue and things like that. And pediatrics are extremely respiratory dependent. And so if anything is affecting their respiratory system, things tend to tank pretty fast. Infections can cause inflammation. That can cause dyspnea by obstructing airflow in the larger airways. So like in this top photo, you've got a swollen pharynx, okay? And that's all of them. That's the nasopharynx, oropharynx, and the larynx. You can have a swollen trachea. Any sort of inflammation or swelling is obviously going to close off that airway, because what is the trachea and the larynx surrounded in? Do we remember? The rings of what?
Cartilage.
Cartilage. Okay. And how much give does cartilage have?
Minimal.
None. It has no give. Especially around the trachea and the larynx. And so if there's going to be any swelling, it can't swell out. And so consequently, it's going to swell in. Okay. And that's going to cut off the air supply. Okay. Which also is going to impair exchange of gases between alveoli and capillaries. In this lower, so this one, she has a swollen pharynx. Here, she has a swollen epiglottis. So epiglottitis is a pretty common infection for small children. And so even though, your epiglottis would be, it's only covering the esophagus, because it's swollen, it's narrowing the airway into the trachea as well. Okay, your esophagus sits in front and your trachea sits. That's a lie. Your esophagus sits in the back and your trachea sits in the front. So, right? Yeah. Yeah. I had to think about that for a minute. Sorry. Okay, acute pulmonary edema. What does acute mean?
Sudden onset.
Sudden onset. Yeah, it happened right here, right now. Not over an amount of time. It's a pretty sudden thing. Okay, so acute pulmonary edema is an accumulation of fluid in the lungs due to an infection, injury, things like that has suddenly developed. Okay, so if we have fluid in the alveoli, this is going to disrupt our gas exchange. Okay. The fluid is going to push against our vessels, and that can close off our vasculature, the capillaries, and so now they're constricted. It's more difficult to perfuse. It's more difficult for gas exchange to happen because it's layering on top of the membranes. That can be a real problem if there's too much fluid because the interstitial fluid or intracellular fluid is pushing out because there's just too much of it, and it has to push out into the empty spaces. Okay. Anybody know a really good tool to use to help push it back where it's supposed to be?
CPAP.
A CPAP. Yep. CPAP, continuous. Oh my gosh. Pressure. Continuous positive airway pressure. Okay. A CPAP is really great to use. There's some contraindications to that we'll go over later. But another thing to understand is that not all patients with pulmonary edema have heart disease. Okay. So we talked about that right-sided heart failure. if there's something wrong with the right side of the heart, then it's going to cause a backup into the lungs. Excuse me. If there's something wrong with the pump on the left side, sorry, this is something I always have to think about. On the left side, if there's something wrong with the pump on the left side, then it's going to back up into the pulmonary veins. Okay. And when it backs up into the pulmonary veins, it backs up into your lungs. And then that is going to cause fluid buildup. Okay. Also, if there's issues with the lungs, that's going to back up into the right side of the heart. And so then you can have right-sided heart failure, depending on where it all starts. Okay. But not all pulmonary edema comes from heart disease. Pneumonia can cause pulmonary edema, just fluid in the lungs, and that is not, has nothing to do with your heart. Not necessarily nothing, but nothing major. Patients who are experiencing pulmonary edema may also present with dyspnea, orthopnea, fatigue, reduced exercise capacity, and pulmonary crackles. Okay, pulmonary crackles is a sound that you'll hear when you're auscultating the lungs. Okay. Chronic obstructive pulmonary disease. Okay, COPD. This is a slow process because it's chronic, it's not acute. It's a slow process that disrupts airways and alveoli. Okay, cigarette smoking is the most common cause for COPD. The obstruction occurs in the bronchioles. That's the smallest passageway right before you get to your alveoli. And chronic bronchitis results from overgrowth of the airway mucus glands and excess secretion of mucus. Okay. That chronic bronchitis is creating irritation, lots of coughing. And so your body is going to compensate for that by creating mucus in order to soften things, in order to get whatever is in it out. That's just the response, is to secrete so that the infection gets out. And that excess secretion of mucus is going to block your alveoli and your bronchioles. Okay. Pneumonia develops when passages are consistently obstructed. So when you have a lot of just sitting fluid in your lungs, and then repeated episodes of pneumonia can lead to COPD because of the infection and the destruction of alveoli. Okay. Emphysema is the most common form of COPD. It's characterized by destruction of alveolar walls related to destruction of pulmonary surfactant. Okay, so that surfactant is the lubricant that helps your alveolar sacs inflate. And without it, it becomes very dry. It loses its elasticity, and so your alveoli break, they rupture, they just degenerate. And so without your alveoli, you can't have gas exchange. And so the less alveoli you have, the less gas exchange there is, making it more difficult to breathe. Okay. Patients with acute COPD, so they're having an episode, will complain of shortness of breath with gradually increasing symptoms over a period of days. They'll exhale through pursed lips. Why? Anybody know?
They're doing a forced exhalation or whatever, they're pushing.
It's kind of like, it's like to control, so what, I want to see if I can explain this. I don't think that's the best way to explain it. What they're doing is they're trying to allow for more time for gas exchange to happen. Okay. So if they purse their lips, it's a smaller opening, or it's a smaller exit. And that allows the lungs to take more time to deflate, which gives your alveoli more time to exchange gases with your capillaries. So because they have very little or less functioning alveoli, they need more time in order for more gas exchange to happen, because if you're lacking in resources, then giving them all the opportunities that they can take to do gas exchange is going to be the next best thing. And so pursing your lips slows that process down, allowing for better perfusion. They'll also present with having a chest with a barrel-like appearance. I never really understood what that looked like until I saw somebody and I was like, yes, that is a barrel-like chest. And I really can't explain it other than it's a barrel-like appearance and you'll know it when you see it. Okay. We talked about this. This is a normal alveoli, normal bronchiole. This is inflammation or infection with the mucus secretions, and air is getting trapped because it's having a harder time coming in and out. And so if you have too much of that, you can either have a full-on obstruction, or you can cause overexpansion of your alveoli. They get stretched out and the elasticity decreases, and so they don't return back to where they were before. So they become dilated and really kind of useless. Okay. Asthma are acute spasms of the bronchioles. This is excess mucus production and bronchiolar muscle spasm. So it's a combination of your bronchi and your bronchioles spasming, the production of mucus in your bronchioles, and edema, okay? That inflammation due to fluid buildup, okay? So a normal bronchiole is going to look like the one on top, and one suffering from an acute bronchospasm is going to look like this, where there's inflammation, there's edema, it's spasming, and there's mucus, excess mucus production, which is obstructing the bronchiole. Okay. This can result from an allergic reaction. You can have exercise-induced asthma, severe emotional stress. You can have difficulty breathing when you're having anxiety or when you're feeling overwhelmed. I'm sure we've all felt it, or any kind of upper respiratory infection as well. Anaphylactic reactions. We talked about this, so I'm not really going to spend a ton of time on it. But that's the dilation of blood vessels all over the body. And that dilation is going to cause a drop in blood pressure, which is going to decrease the perfusion, the ventilation perfusion ratio. And that can cause death, right? And it can happen very quickly as well. A spontaneous pneumothorax. We talked about kind of the bathing suit analogy when it's suction to your skin. That's how our pleura is. This is what happens when you introduce air, okay? It ruins the pressure gradient and the pressure ratio of or inside your thoracic cavity, okay? So either you can have a wound, so stab wound, someone stabbed you and they pulled the knife out, and now there's a gaping hole in your chest, or a bullet. There's a hole in your chest for whatever reason, and now air is getting in that way. Or you can have a punctured lung, and now air is escaping into the thoracic cavity from your lungs. Or you can have both if you're especially unfortunate, okay? This can be caused by trauma or even medical conditions. But in either case, you're going to hear diminished breath sounds on the affected side because there's the pressure is messed up, and so there's no inflation, and there's no oh my gosh, what's the opposite of inflation? Deflation. We're doing good, okay? No deflation, so there's no air movement happening with your lungs on the affected side, okay? Hello? Patients will become acutely dyspneic and typically complain of pleuritic chest pain. especially if it's a trauma. I mean, there's going to be a lot of pain there for many different reasons. Okay, but pleuritic chest pain is the grinding of the pleura, the visceral and the parietal pleura against each other. And that's extremely painful. Some severe findings are going to be altered mental status because there's less oxygenation in the blood and to the brain, cyanosis and tachycardia, unilaterally decreased breath sounds, so decreased breath sounds on one side, local hyperresonance to percussion. So when you percuss the chest cavity, you're going to have hyperresonance on the affected side because there's more space, there's more air, there's room for those sound waves to bounce around. Okay. Subcutaneous emphysema. So that's going to be kind of emphysema just in the skin above it because air is escaping. And then tracheal deviation is an extremely late sign. Okay. And that's because, especially if you have pressure building inside the chest cavity because there's air and there's no escape for it, then the constant air being introduced to your chest cavity is going to push against the rest of your chest cavity. So your lungs, your heart, and eventually your trachea is going to deviate to one side. And so if your trachea is deviating to the left side, then you've likely got an affected right side. Okay. But that is a very late sign. A pleural effusion is a collection of fluid outside the lung on one or both sides of the chest. Fluid can be from irritation, infection, or even cancer, and it should be considered in patients with lung cancer and shortness of breath. There's not a ton we can do for that, I don't think. You're going to hear decreased breath sounds over the region of the chest where fluid has moved the lung away from the chest wall. And so if you look here, we've got fluid here. You might hear some breath sounds here because, you know, there's still gas exchange happening here. There's still ventilation. But if fluid is pushing the bottom of your lung, of the lobe away from your chest wall, then you're not going to hear anything here because there's no exchange happening there. It's filled with fluid. Okay. Patients usually feel better when they sit upright, and that has to do with gravity, right? So if you're pushing all of the fluid to the bottom, then it becomes a lot easier to breathe because nothing's pushing on their lungs from the top. Okay. And definitive treatment is fluid removal, and we do not do that. So that's a treat with diesel sort of thing. Oh. Excuse me. Pulmonary embolism is when a blood clot circulates through the venous system and travels into a pulmonary artery. This is caused by a clot formed in a leg vein or a pelvis, and it decreases or it completely blocks blood flow in the lungs. Okay, this is very, very bad. This can also occur as a result of damage to the lining of vessels, hypercoagulability, which is a high probability of blood clots, or slow blood flow in a lower extremity. So sedentary lifestyles or somebody put on bed rest. So there's just little to no, not to know, but little blood flow in the legs because they're not using them. There's no movement. And then if they suddenly start getting up and moving around, that can dislodge some clots and those can travel to the lungs. Okay. So those risk factors include immobilized legs, recent surgery, pregnancy, oral contraceptives, infection, cancer, sickle cell anemia, prolonged inactivity, and being bedridden. Okay. So lack of movement in general. Or congenital problems. Signs and symptoms are dyspnea, tachycardia, tachypnea. What is tachypnea?
Fast breathing?
Fast breathing.
Fast breathing. Very, very good. Varying degrees of hypoxia, cyanosis, acute chest pain, and hemoptysis. Okay. Acute chest pain, many times. So like when you have someone who's complaining of chest pain that's of cardiac origin, it's more of crushing. It's more of something sitting on them. And it's like in this area, right? Or it just feels like it's tied around my chest. But in a pulmonary embolism, a lot of times they can say it hurts right here. It hurts right here. They can pinpoint a spot where it hurts really bad. And that's a pretty good sign of a pulmonary embolism, okay? Obstruction of the airway. Patients with dyspnea can have a mechanical obstruction. That can be food. It can be the tongue. A lot of times if you're laying on your back, this is sometimes this is a cause of sleep apnea. It just kind of closes off the airway. Or it causes snoring. Okay. In an unresponsive patient, this may be the result of vomit, a foreign object, or the tongue. Okay. And so that's where your suctioning and your OPAs become really helpful. Oh my word. I can't see the top. What does that even say? Hang on. Environmental industrial exposure. Sorry, there's the Zoom bar that's sitting in front of that. Okay. Pesticides, cleaning solutions, chemicals, chlorine, and carbon monoxide. These can all affect our ability to breathe in various ways. The amount of damage largely depends on the water solubility of the toxic gas, okay? Or how well the gas is able to perfuse into our bodies, okay? Highly water-soluble gases cause swelling and irritation, okay? Because those can make it into our alveoli and perfuse pretty easily. And so it's going to cause that irritation and that swelling. Less water-soluble gases may cause pulmonary edema up to 24 hours later. It just takes a little longer to take effect. Cystic fibrosis is a genetic disorder that affects the lungs and digestive systems. Symptoms range from sinus congestion to wheezing and asthma-like complaints. Look for respiratory insufficiency, signs of a respiratory infection, and intestinal blockage. And this often causes death in childhood. In pre-hospital settings, it's a little hard for us. I mean, obviously, it's never our job to diagnose anything. That is outside of our scope of practice, is to diagnose. However, we do want to be aware of medical histories and symptoms of some common things, so like cystic fibrosis, and we can suspect things, and that can lead us to treatment options. Okay, so obviously, like, we can't know for sure if there's an intestinal blockage, but we certainly can look for signs. Okay. Some age-related conditions. Bronchiolitis is an inflammation of bronchioles due to a viral infection. This is caused by metapneumovirus and respiratory syncytial virus, or RSV. That's been a real problem. RSV creates an infection in the lungs and breathing passages, and it is highly contagious. Okay, I think they were having more issues with RSV last year than they were COVID, but don't quote me on that. That actually you'll also see a lot of RSV in pediatric patients. Croup is another very pediatric dominant problem. This is due to inflammation and swelling of the pharynx, larynx, and trachea. And it's often secondary to acute viral infection of the upper respiratory tract. Okay. Hallmark signs are stridor and a seal bark cough. So, my really awesome presentation had a video that showed you those things, but alas, I cannot show you those things. So I would YouTube signs and symptoms of croup, because those are very, very telltale. Or if you've had children or no children that have had croup, it's pretty easy to see and diagnose that. Epiglottitis is the inflammation of the epiglottis. It's usually caused by a bacterial infection that produces severe swelling of the flap over the larynx. The patient will appear very, very sick. This is a bacterial infection. Your histamines are going to be going crazy, and it's going to be difficult to breathe. Okay, so you're going to have a sore throat, high fever, stridor, high-pitched inspiratory sounds because of that upper respiratory or upper airway obstruction. And there's going to be tripod positioning and drooling because of the difficulty breathing. That tripod positioning is going to, that's kind of the body's innate way of trying to open up the airway as best as possible. Pneumonia is that ventilation disorder caused by an infection of the lung parenchyma. Young children and elderly are at the greatest risk for these. It presents as a localized infection in the lungs, and it can become systematic. Signs and symptoms are a fever, chills, productive cough with purulent sputum, pleuritic chest pain, and excessive mucus. There is pneumonia where you are bedridden. They also have walking pneumonia, if anybody's ever heard of that. Back before COVID was cool, they told me I had walking pneumonia. I actually had COVID. So, but they were like, we don't know what it is, but it looks like walking pneumonia. And it was absolutely miserable, but COVID is miserable. However, I do know someone who did have walking pneumonia, and it's horrible because you feel horrible, but you feel just good enough that you can move around and like do stuff. But it can be very hard to breathe. Pertussis is a highly contagious airborne bacterial infection. Mostly affects children younger than 6 years, and you present with cold-like symptoms, but coughing spells can last for more than a minute, and coughing spells can inhibit gas exchange, do inhibit gas exchange, and so that can be very dangerous. They're feverish, and they have a whoop sound on inspiration after a coughing attack. And so I think pertussis is the one that's also called a whooping cough. And it's because of that characteristic whoop sound on inspiration after a coughing attack. Airway obstructions. We always want to consider the possibility of a foreign body when a young child becomes short of breath. Children from birth till pretty late in childhood will put things in their mouth, and that is how they discover. That is their way of discovering new things, is by putting it in their mouth. And so if you have a child with difficulty breathing, then we always want to suspect the possibility for a foreign body, just because that is something that they may have done, put something in their mouth, and now it's gotten lodged and created either a full-on or a partial obstruction of the airway. Tonsil inflammation can also partially occlude the airway, in that you'll also find that in younger children. Dysfunction of a tracheostomy can create an upper airway obstruction, and obstruction may be in the lower airway due to tracheal trauma, lung disease, mucus accumulation, or a smooth muscle spasm. Okay, so an airway obstruction can happen in your upper or even your lower airway, and we just need to be aware of that. Heart failure is when your heart muscles are either injured by a heart attack or an illness. Tissue can start to die. They're just not getting enough blood perfusion or oxygen. This will result in pulmonary edema because there's just not as good pumping happening to your lungs and from your lungs to push things out of your lungs. Okay. Risk factors of heart failure include hypertension as well as a history of coronary artery disease. Your signs and symptoms include difficulty breathing with exertion, a sudden attack of respiratory distress, feeling suffocated, or cold sweats and tachycardia. Okay, wet lungs versus dry lungs. Your wet lungs are going to be associated with pulmonary edema. That makes sense. Your dry lungs are associated with COPD. But your breath sounds are going to be super helpful. They can also be very confusing. So they're not definitive. They're to help guide us in the right direction, but it's most important. Just like we don't want to treat the monitor, we want to treat the patient. It's the same thing with our breath sounds. Treat the patient and not the breath sounds. Okay. All right. Okay, we'll practice this more during our skills boot camp, if needed. But when you are auscultating breath sounds, you want to make sure that, if possible, bring your patient to a sitting position so you can access all of the points. And we also want to do what we can to make sure that the stethoscope isn't in contact with the skin, okay? Because that will make it so that there's less muffling of the breath sounds due to clothing being in the way. Okay, so we're gonna go our upper lobes and the lower lateral lobes of our lungs. And then in the back as well, we can get pretty high up on our lungs without, like on this side, the heart being in the way. And this will give us a pretty good idea of how well air is moving through the lungs. You have several lobes in your lungs or for your lungs. And so you want to make sure that you're getting a good picture. The other thing you do is you compare from side to side, okay, one at a time. So we're not going to go upper right, upper left, lower left. We're going from upper right to upper left, lower right to lower left, okay? Because we want to make sure that we're comparing both sides in the same anatomical position. Making sure that breath sounds are normal or abnormal. You can hear crackles, rhonchi, stridor, wheezing, pleural friction, rub, or snoring sounds. I like to play a video during skills boot camp when you're having to cross off that skill or pass off that skill, and it's pretty helpful. So I would study this by looking up YouTube videos, but we'll also go over it in skills boot camp. Sample history, pertinent medical history becomes really important. Possible allergies, how long has it been happening? Trying to see. Okay, so some emergency medical care. We're not going to be able to finish this, but I will do my best. Emergency medical care, we want to make sure that we're giving oxygen, okay? We're doing everything we can to get their oxygen above 94% and giving that psychological support that can also come in forms of coaching their breathing as well, okay? Doing your best to decrease their work of breathing so that they don't wear out quite as fast or at all. We want to make sure that we're trying to remove restricting clothing. Even if a patient can walk, we don't always want them to walk because that can increase the work of breathing. And then a lot of times being in a semi-Fowler position is a lot easier on a patient. For COPD patients or emphysema patients, a lot of times sitting up is a lot easier for them to breathe. Providing oxygen. We talked about avoiding 100%. Administering a bronchodilator. So like our albuterol treatments or if needed, epinephrine. Bronchodilators are of little value in treating conditions such as pneumonia, pulmonary edema, and heart disease because those are dilating the bronchioles and constricting the vasculature of the body, when in those situations, that's a fluid problem and your CPAP is probably going to be better, okay? Respiratory medications are the most common are your inhaled beta agonists. Secondary bronchoconstriction can be reversed with bronchodilator. So just kind of like we talked about with epinephrine and albuterol. Even though with epi, it's mainly a vasoconstrictor and secondarily a bronchodilator. Your albuterol, it's mainly a bronchodilator while also being secondarily a vasoconstrictor. Okay. But being aware of your common side effects of tachycardia, nervousness, and muscle tremors. Epinephrine can be nebulized, but just keep that in your thinker, and that will likely be gone over later with Michelle. Okay. We talked about this. Aerosolized therapy, this is your nebulizers. You need to make sure that you have the medication and access to constant oxygen flow in order to nebulize it. Those are your metered dose inhalers. We know what those are. You want to make sure that you're constantly reassessing your patient, because if they become fatigued, breathing might need to be supported more aggressively. We had a patient who was in status asthmaticus for, I think when he was with us, I think it was like 45 minutes to an hour. And that just means he was having a constant asthma attack for 45 minutes to an hour. And that's extremely dangerous. And he got very, very tired to the point where he would stop breathing and we'd have to like sternal rub him and he would gasp awake and then start hyperventilating again. Eventually, AirMed had to intubate him, which is a last resort in all situations, but also because sedating is not good for asthma. But in that case, they wanted to give his lungs a break and he was intubated for like 2 or 3 days. We bagged him for a little while, but then being aware of any gastric distension and vomiting, that can happen from ventilating too aggressively. So be aware. CPAP is used to treat obstructive sleep apnea and respiratory failure. Many people with obstructive sleep apnea wear a CPAP unit at night. There's a lot of people. I think that there's like more and more. I find more and more, but that may just be because I'm getting older. This increases pressure in the chest, which expands the alveoli. It also will push fluid out of the alveoli and back into the tissue. And be vigilant about monitoring the gas supply. We want to make sure that we're giving them the right amount of oxygen, the right amount of pressure, and that we're not killing their blood pressure or their mentation. Okay. Bilevel positive airway pressure is similar. This is one pressure that can be delivered during inspiration and a different pressure can be delivered during exhalation. This causes a pressure variation in the chest, which allows for more normal blood flow. It is more complex and it is more expensive. I'm going to stop here. I'm not even sure where we are on this. Hang on. Oh, you know what? We're really close. Okay, we're going to do this in 10 minutes and it's going to be great. Okay. Upper and lower airway diseases, patients present with signs and severe respiratory impairment. Obviously, your chief complaint is still going to be dyspnea. They might have a cough, or they might have difficulty breathing at night when they're sleeping, okay, or trying to sleep. There can be wheezing. There can be various lung sounds, but the most important thing is that we're placing a patient in their position of comfort. Whatever they feel like helps them breathe better, that is what we want, because we want them to breathe better, okay? Making sure we're constantly monitoring their airway. We apply high flow oxygen as needed and assist ventilation if needed. And then we make sure we transport and contact medical control if things start to go south and we want to administer some other interventions. Acute pulmonary edema, this can be associated with cardiac disease or lung damage. We want to give 100% oxygen, okay? 15 liters of oxygen, be an honorary breather mask if we need. We can carefully suction any secretions from the airway. We want to make sure that we're not suctioning for too long at a time. Otherwise, we're basically sucking out all the oxygen that we're trying to give them. Assist ventilations and establish IV access and monitor flow rates carefully. Reason being is if they have pulmonary edema, there's a fluid problem. And if we're giving them too much fluid through an IV, we're going to exacerbate that issue. Aspirating is inhalation of anything other than gases. This is a killer. This can kill people very easily. We want to make sure that when we are ventilating a patient, we're avoiding gastric distension, and we aggressively monitor a patient's ability to protect their own airway, okay? As well as treating any aspiration with suction and airway control if we're unable to do anything else, okay? So being aware of any recurrences, a lot of times aspirating vomit is a big killer. And so putting patients on their side, having suction ready, because once it goes down the tube, there's not a whole lot that we can do about it because we're not respiratory therapists. Okay, COPD, patients often find breathing difficult while lying down. If they have a prescribed inhaler or a CPAP, we want to make sure that we are helping them with that, okay? Asthma can become critical, as I was just saying. We want to constantly assess our patient and their ability to maintain their own airway. This is a recurring condition, and the three components of an asthma attack are a bronchospasm, airway edema, and increased mucus production, okay? We can't treat all of those, but we can treat some of it with a bronchodilator, okay? And then be prepared to suction. If we are having to assist in their ventilations, we want to make sure that we're using gentle breathing, okay? Something that might be helpful to you is if you're the one bagging a patient, breathe with them, because that will help you help them. Not to overbag them, not to bag them too fast, or to make sure that you're bagging them enough. Bag them at the same time that you're breathing, and that will help them have the right amount of ventilations, but it will also help you to stay calm. Emergency care of a child with asthma is the same as an adult. Status asthmaticus is a dire medical emergency. They can tire out very quickly, in which case they will stop breathing, okay? Aggressive airway management, oxygen administration, and prompt transport are essential. We talked about anaphylaxis. We talked about pneumothorax. Talked about pleural effusion. We can't remove the fluid, okay? So a lot of that is treat with diesel, which means drive fast, okay? And a pulmonary embolism, someone can go into cardiac arrest pretty quickly with a pulmonary embolism. So making sure that we're ready to initiate CPR if needed. And then hyperventilating can be caused by life-threatening illness or panic attack. Make sure that we're giving oxygen and we transport. This is a really great opportunity for us to provide psychological support, especially if it's due to anxiety. And coaching their breathing through that box breathing is going to be really, really helpful, okay? obstruction, trying to figure out what the obstruction is. If the patient can talk and breathe, we want to make sure that we're providing oxygen and we transport. There's not a whole lot much else we can do. If we can remove the obstructing body, then we should, but only according to basic life support guidelines. Okay. No blind sweeps. We're not reaching down somewhere that we can't see. We are removing according to our protocols and not beyond that. Okay. Cause you can do a whole lot more damage, than good if you're working outside of those protocols. And then administering oxygen. Any exposures, making sure that we're contacting any kind of teams that need to be notified. If it is environmental or industrial or chemical or anything like that, making sure that you can get access to a safety data sheet. A lot of times those can inform you what to do in instances of exposure, okay? Once a patient is decontaminated, gather information on substance and cause of dyspnea, provide 100% supplemental oxygen or assisted ventilation if necessary. And if the upper airway is compromised, aggressive airway management may be required. Once the airway is gone, it's gone. So this is good, especially now that you're becoming advanced. We have access to advanced airways. We can't intubate, but supraglottic airways can be really helpful in some situations. And so knowing when to be aggressive about that treatment is really important. Okay. Bronchiolitis, this is entirely supportive treatment. We're supplying oxygen, and if we need to assist, then we'll assist, okay? RSV, looking for signs of dehydration, and then treating any airway and breathing problems, okay? Also supportive. Croup, will respond well to humidified oxygen. Position of comfort is really important. And avoiding agitating the patient. And if it's a child, that can be really hard. I spent probably like 30, 45 minutes with an 18-month-old who was, I think he was like pre-RSV or some sort of respiratory infection. And the internet connection was really bad. And his mom was trying to play Miss Rachel videos. If anybody's heard of Miss Rachel, she's a human development anyway, she's great. She's delightful, but it wasn't working. And so I spent like 30 minutes singing to this baby in order to keep him from getting overly agitated so that they could give him an albuterol treatment to help him breathe. It was cute. It was a lot of fun. Epiglottitis, same thing. Supportive, avoid making it worse. Pneumonia, supportive. Administration of IV fluids may help, but you do want to be careful. You're not giving too much, okay? If the fever is present, cool the patient down, and you may follow your fever protocols, okay? And then, of course, with pertussis, children really should be treated in the hospital, especially because of how contagious it is. And replenishing fluids, administering oxygen, clearing airways and airway obstruction obviously is ideal if we can do it. Otherwise, we need to be finding some alternatives pretty quickly, especially because with children, they're very respiratory dependent. And so we need to make sure that their respiratory system is as uncompromised as possible, okay? Any kind of heart failure, high blood pressure and low cardiac output often trigger sudden pulmonary edema. And so our treatment should consist of an adequate airway, ventilation, and circulatory support, okay? Oh, tracheostomy dysfunctions. We don't mess with the home ventilator. We don't touch the settings. If it comes with us, then we leave it that way and we don't touch anything with it. It can be very temperamental, very sensitive, but making sure that a patient has an airway, a position of comfort, and that we have access to good suction, okay? Once the obstruction is clear, a lot of times it can just be sputum. will oxygenate the patient and treat based on presentation. Establishing an airway patency is the immediate goal for geriatric patients, and really honestly for any patient. Their airway needs to be patent for them to live. So if there is a tracheostomy dysfunction, we need to be very careful with how we're treating the trach. Okay. If there's sputum right there, then let's use suction, see if we can clear it up. But we are not respiratory therapists, and that is not our scope. And so you need to be really clear with what is in your scope and what is in your protocols as to how to treat any sort of tracheostomy dysfunction. Okay. And then when concerning epidemics or pandemics, your PPE is going to be your best friend. Epidemics are, excuse me, I lost my train of thought. Occurs when new cases of a disease occur in a human population, substantially exceed what is expected based on recent experience. But a pandemic is an outbreak that occurs on a global scale. Okay. Many serious diseases can be passed by the respiratory route. Okay. Influenza is one of them. PPE is no joke. Please wear your PPE, because it's extremely, even if you are able to fight the illnesses, if you are a healthy human being with a healthy immune system, you can be a carrier and you can compromise someone else who may be immunologically compromised and can't defend themselves and will become sick. So wear your PPE, be responsible. Okay. Get your vaccinations. Please be responsible. If you don't think you should get your vaccinations, then let's chat and we can have a nice conversation about why you should get your vaccinations. Okay. And then of course a HEPA respirator or a PAPR machine as well during aerosol generating procedures. So just knowing what you have access to and make sure that you're using it. Okay. We did it, everyone. And we only went 3 minutes over. I'm so terribly sorry. Are there any questions for me? No questions? We are all experts on airway management and respiratory emergencies. I love that. Fantastic. If you guys think of any questions, don't hesitate to jump on the GroupMe chat. I'm sure any sort of question that you might have is probably something that somebody else has wondered, and we can all do well with sharing our collective knowledge. Okay. Otherwise, complete your assignments. Make sure that you stay up on your quizzes. And I always want to bring up your AMP mod assignment, because that will bite you in the butt if you leave it to the last minute. It takes time, a lot of time. So you guys have started that, right? Do we know what that is?
Yeah, she talked about it last class.
Okay. All right. Yeah. So get started on it so that you're on top of it. Otherwise, you'll hate yourself forever. So, okay. Well, if there's nothing else, you guys have a super great day and we'll see you next week.
Thank you. See ya.
Thank you, Morgan.
Thank you.